Megger India team for bus bar differential testing. And then with Mr. Muhammad Rashad, he's presenting our distance testing protection. It seems that I'm not sharing my screen. Would you please just give me the presentation, right?
You're already with the presenter.
Okay.
You can just share your screen.
Okay. I hope everybody can see my screen. So yeah, for our agenda today, continuing from where I left, and then it will be me presenting line differential testing. I have a very good news for everyone who was waiting for us to release new things about this. For the second day, it will be mainly focused on smart grid and digitalization and power systems. I'll start first also by me talking about sampled value testing. It will be a quick and brief introduction in that big topic. And then it will be with our specialist from Sweden, Mr. Andrea Bonetti, talking about digital twin technology and testing protection systems. It's a very fascinating topic, and I urge everybody to see it. It's a really game-breaking thing. And then at the end, we will end with a session about traveling wave and time domain-based protection, presented by Engineer Muhammad Ashraf from Schweizer Engineering Laboratories. So quick introduction about each and every presenter that we have. For the first day, we have Mauro Borelli. He is a senior application engineer from our Dallas team, Megger Dallas team. He has been an expert on protection testing for more than 20 years. Worked previously in companies like ISA and Dobel in developing and training and sales for protection testing solutions. So his expertise are really very well in the protection testing field. And then we have Dr. Dinesh Babu from Megger India team. He is very well known in the Indian region. Been previously working for companies like GE and ABB as product manager, and now as a product and application manager for the Megger Indian team. For the rest of the day, we have Engineer Muhammad Rashad from Al-Fanar Engineering Services. Thank you for joining us on this event today. He is the technical training section manager. He has quite the experience in testing power systems and protection testing, switchgear, transformers. And then it will be me presenting the last session today for line differential. I have been working with Megger for about 3 years now as application and sales engineer, mainly specifically in protection testing. I have conducted many webinars. If you have joined us before, you might have heard of me. For the second day, we have Andrea Bonetti. He is also joining us today here as a panelist. Thank you for that. He is a senior specialist and product manager for our Megger Sweden manufacturing site. He has a quite extensive knowledge in standardization, especially IEC standard, and have worked in many conferences and in many standardization. For example, the IEC 6150, he was one of the specialists who joined in developing and writing that standard. And we have Mr. Muhammad Ashraf from Schweizer Engineering Laboratory. Thank you for joining us today here. He is a protection application engineer, has a 13 years experience in the field of electrical protection, and have served many roles in testing, commissioning, design, and application development for high voltage and extra high voltage protection system. He will be talking about the known traveling wave technology that SEL have developed for a quick and very fast tripping and also fault location. Finally, I would like to urge everyone that since we have quite the panelists today, to feel free to ask any questions, and we will sure answer them at each question and answer session. It will be mainly after each topic. The presenter will answer all the questions related to that topic. And if anyone have any question regarding the protection system as well, feel free to answer or ask that a question, and hopefully we will be able to provide you with answer for that. So with that, we will start our event now by introducing Mauro Porelli. So Mauro, you please open your camera and I will give you the sharing rights for your presentation. Hello, Mauro. It seems that you are muted. Mauro, it seems that we cannot see your screen or hear your voice. Would you please unmute?
This is what I'm trying to do. I don't know what's happening.
We
can you
can
hear me
see
now?
your mouse moving, but
Okay, now I'm supposed to be unmuted.
yes,
Okay, can you hear me?
yes, we can hear you
Okay,
clearly.
I'm very sorry. I lost the I lost the controls of that.
It's okay.
All right, so sorry for this first let's say, scenario at the beginning. So we will be talking about power swing and Autostep. Why we're talking about this topic here? Because it is something that has been always a big issue to test. It's because we need to inject something like a swing of voltage and current and simulate the conditions for the relay to understand what's going on in the system. Usually, we will talk about the basic power system stability, what causes Autostep and power swing, and what does the relay really see when this happens, and the relay detecting method. And then we will talk about our techniques to generate the power swing and Autostep. So, what is the problem in the system? So let's make something simple. In the system, what happens is that in general, two regions or one generator connected to a region with their own source impedance and remote impedance together with as line impedance of the connection, exchange power based on this formula that you see here. The power is the product of the voltage divided by the total impedance time the sinus of the delta angle between source 1 and source 2. So if the angle is 0, then what is the sinus of 0 is 0, so there's no power. So in order to exchange power, you have to change the angle, right? But of course, you cannot change too much, because if you change too much, you reach the so-called unstable condition. So there's a situation where the impedance is at its optimum when the delta, the angle between the voltage of generator 1 and generator 2, or source or remote, exceed a certain angle, you move to the unstable condition. So in general, we are talking about moving on the first part of this sinusoidal waveform. So the delta is actually the rotor angle between source and remote. This is rotor angle is not the mechanical angle, although it is related to that. So it is the electrical angle between source and remote. Now, what happens when there is a fault? When there is a fault, there is, in general, there is a loss of power flow due to the loss of the load. So one generator, which is being pushed by a turbine in the back, will start pushing more, and then this will cause the generator to accelerate, right? So the frequency increases during the fault and the angle advances. If the angle advances too much, it can reach a certain position. If the fault clearance is in that position, then we are not yet after the peak of this sinusoidal or this sinusoidal curve, I may say, and then it will decelerate. All right. So if the area 2 is less than area 1, then it becomes unstable. That means the generator will lose the grip with the system, and it will actually accelerate, and it will make the so-called unstable swing, which is also called Autostep. If the area 2 is greater than area 1, so the green is greater than the red, then it becomes unstable. So the generator is able, it will have some some disturbance in the angle position, but it will return to the normal position, and probably if it is cleared in time, it will return to the position P0. So this is called then stable condition. So we can call these two phenomena as the first one, unstable, is the so-called Autostep, and the second one is called the power swing. So this is very important to remember, because sometimes I've heard some confusion between Autostep and power swing. So it's very important to understand this concept. So basically, what happened is that's the same. So for a faster fault clearance, it will increase the stability, because the area 1 will remain close. So if you have a slow fault clearance, then it will get this area 1 to grow and become very big. So the faster you clear the fault, the more stable the system is. So in general, this is the situation. So when the area 2 is too small, then you get a very it is very likely to have one power swing. Sorry, Autostep. So that is the condition for an Autostep. The power swing is the other condition where the area 1 is smaller than area 2, and then the generator is able to recover the position that it's just a swing in the power. So that's the reason why it's called the power swing. So it goes up and down a little bit. So here, this is a fault, a real fault, which has been recorded long ago. Actually, this is a record that I got from Peru. As you see, there is a fault at the very beginning, and the fault is cleared after a very long time. You see, it's about 0.4 seconds. So it went up to second zone, right? So after the second zone in 0.4 seconds, the generator lost the grip with the rest of the system, and started swinging until another protection, the power swing protection, operated the relay and disconnected the system from the line. So as you see, it is a typical combination. As a fault, it cleared very slowly, and during the fault, it's also here at this position, it started just a laser pointer. So in this position, it started already with losing the stability, right? And then here is where it actually happened, the full power swing. So what does the relay see in general when the relay is working at the normal condition? The frequency is the same for both generators, so the two vectors are turning at the same speed. This is normal situation. But when there is a difference in frequency, then one generator runs at a different frequency, right? So as you see, the phase angle between voltage and the source and the voltage on the remote location are changing. So there is a change in the phase angle between the two voltages. At some point, the phase angle are in phase, and at some point they are in opposition. And these are generating that swing that we have seen before, where the current goes up and down, the voltage goes the opposite way, down and up, down and up. And this is what the relay is. What the relay will see here is that it is actually the voltage divided by the current seen at this position, and the voltage is a combination of two sources at the same time in this position. So actually what happens is that if we apply the effect of a superposition, so in the local position, the local current, the local generator is creating a current which is ES divided by ZT, where ZT is the sum of this of the two sources plus the line impedance, and the remote is the current generated by this generator. So in the end, the composition of these two currents is the sum of these two, and the same for the voltage. So this gives us the idea that we could apply the effect of superposition with our software, which is capable of doing this. So in our software, we have the possibility of setting two different waveforms. So we have a waveform number one here with the 50 Hz and 50 Hz, and these are the current, these are the voltage, the phase angle, etc. This is for the to simulate the effect and the relay position due to generator number one. The generator number two will do the same, but it's got, let's say, a different frequency like 48 Hz, and this different voltage and current. So these two are generated together in our software, and the effect is that this part of voltage and current are the effect given by generator one, or the source generator, to the voltage and current in this position, and this is the effect of generator number two. And as you see, due to the fact that you have a lot of impedance here, so the voltage is less in this position because we have more, we have the full line impedance plus the remote impedance. It depends on the condition of source and remote. So what does the relay see in the position S is actually, so if this is the impedance seen by the relay, it will see something that moves around. So the relay will see an impedance which is moving around a sort of round line, right? That is actually, there are some characteristics that you have to consider. There is a so-called electrical center, which is exactly the half of the total impedance, and we have a line that passes through this electrical center. We have to consider this, and this is the line when the voltage of the source and the voltage of the in the remote condition are exactly the same value. So when they are the same, there's some point where there's no current at all because they are in opposition, 0, 180 degrees, sorry, 0 and 0 degrees. And that means that there's no current, so you have only voltage and no current, so the impedance can go up to infinite, right? So that's why it is a straight line. When the voltage is, so this is a condition, so when the source is greater, the voltage of the source is greater than the voltage of the remote generator, then we have this impedance that we can call impedance locus at this point. When is the opposite ES less than the ER, then the impedance will run on this side. When they are the same, and then it's just a straight line, but this will never happen. It can be either greater or lower. So in general, it depends on depending on the ratio, you can have a lot of these trajectories for different voltage ratio. So in general, the effect of an unstable swing or autostep is an impedance that goes around this path, and it goes inside the characteristic and then goes outside of the characteristic on the opposite side. So it goes in and out, right? Because it is unstable, it goes around. When it is a stable swing, then the impedance seen by the relay, it goes inside at a certain point, and then it goes out. So this is the so-called stable swing, and they are treated in different ways by different protection, generator protection and distance protection. They are using similar method to detect what is going on, but they will operate differently. So in case of no special protection against power swing, if we're talking about a distance relay, when the impedance goes inside zone 1, then the impedance relay will trip. This is because the relay is done to do this. When the impedance is below a certain value, then it trips, unless it is blocked by something else, which is the power swing block, right? Or auto step block. So zone 2 may trip in case there's no power swing blocking or auto step blocking, if there's no block for power swing and auto step. So for distance relays, what we want is that the protection is blocked to allow in some time to see the impedance recovering its position. But in case, of course, in case the impedance stays stable in zone 1, and then of course it will trip. So this is also related to the setting of the relay. So we need to control the operation of the relay when such event occurred. So this is extremely important to avoid misoperation or unwanted operation. So we don't want a relay to trip for the swing because it is not a fault in the line, and the line protection is protecting against a fault in the line, not against a power swing or auto step. Something else will have to be done in those cases, because of course they are not normal conditions. So the relay detects the power swing in different ways. There's the swing center voltage, continuous superimposed, continuous impedance, these delta Z, R dot scheme, etc. I will not focus on this this method too much, because in the end the idea for the relay is to detect what the relay is doing when to detect that there is a power swing. So the continuous impedance, it will measure the delta impedance during the time, and this is the typical method used by the relays. And the characteristic of the relay is normally determined by a sort of blinders. As you see, there are several blinders, and what the relay does is to detect when the impedance cross one particular blinder, and then when it crosses the other blinders, to determine the speed of the impedance. That means for different protection, for ABB, for Siemens, for Schneider, for any Alstom, etc., they have different ways to determine the powers, to detect the power swing. So it's so so you have so many different shapes that you really need to understand which one is best for you, and of course it depends on the relay. So what happens to the impedance during a power swing? Does the impedance moves slowly across the RX plane, and but there's a fault. It's something different because it's extremely fast. So a power swing is very slow, a change in the impedance, and a fault is an extremely fast change in the impedance. So this gives the relay some hints on how to treat them. So there are, this is the way it works. There is the inner blinder, outer blinder, and there is the relay will measure the time that the impedance takes to cross the two blinders. So first point and then the second point calculates the time. If the time is greater than a certain value, then it will be assessed as a power swing, accepted as a power swing. Otherwise, it will be accepted as a normal fault. So, and now how to test. And now we know what the relay needs to see to detect the power swing. And for to simulate this feature with the testing instruments, there are several ways. EMTP programs. You can simulate also with devices like Opel RT or RTDS or similar devices. You can create a contract file, and the contract file can be just your model in your you can have an Excel sheet that does the simulation, and you can make as many scenarios as you wish. You can also use a stage sequencer, which is in general not accurate, but in some algorithm may not pass this this method. But in general, it's been used a lot, and depending on the duration of the state, this can be used. And then superposition of the waveform, which is what we normally use for the Autostep. So this is the this is what we have in our software and hardware. So analysis of the waveform. This is in general what we are expecting to see out of our simulation. Something like the voltage goes down, the current goes up, and the vice versa. This is the typical waveform that we can see. And if you remember the picture that I was showing you before, it's similar to this. So to simulate this, what we need to do, we need to have the characteristic of the source 1, the source 2, the impedance, the line impedance, and so we need to specify the voltage and phase angle and the frequency of the two sources, the source impedance and the remote impedance plus the line impedance, and then of course you remember then the delta voltage between source 1 and source 2 will determine how much reactive power the two systems are exchanging, and the angle, because that depends on the delta angle of the machine, or the angle delta of the machine. You remember, when the angle is 0, there's no active power. When the angle is 90 degrees, you are at the edge of instability. When the angle is in the range of 30, 40, you are in a normal operating condition. And of course, the delta frequency that will determine the swing. This is how we do the power swing, the Autostep with our software. This is a new method where, as you see, we set the source impedance in this condition and the line impedance, and then we can also select whether it is a strong or normal or weak source impedance, which is a ratio between the source impedance and the line impedance, and then the voltage in the two sources and the phase angle, and then the frequency of the two sources. So this will be used to calculate the electrical center, which is exactly half between ZL plus Z source and Z remote. Okay, so so it goes to 2.5. You can specify, if you like, the position of the electrical center as a percentage of line impedance, and then these are the currents calculated during the swing. This is the load current that depends on the voltage and the impedance. And here you can select the pre-swing condition time, and the number of swing. The period is depends on the difference in the frequency, which is here, and then the number of swing, and this is swing time is what is the total time for the swing. So we will generate 2 swings, and then after that we can apply some post time, and the total time is this one. We can also here in this part of the software a certain number of timers you can assign to the trade, to the block, to whatever you like. So this is how the it works. So the impedance characteristic that we see here is comes from the relay setting. So in our software, the so-called the COF, click on fault, we can import X3 or any setting file, draw the characteristic, and this is shown in this part of the graph. So superimposed impedance locus. So we have the impedance locus. So you can see exactly where the impedance locus is moving. So you might be interested in setting the parameters here, voltage, current, impedance, etc., in order to have the impedance to run through zone number 1, as you see here, just for testing the characteristics, the features of the relay. So, and here, of course, we can set the difference, the voltage difference, the phase angle difference, the frequency, the number of turns, then maximum current if you don't want to grill your relay. Imagine you have a 1 amp nominal current relay, and remember that our instrument can inject up to 60 amps. So that can be quite uncomfortable for the protection. So then maximum the position of the impedance center and the timers expected values if you have something. If not, you can just keep it free. And now the superimposed waveform can give you a good let's say controlling possibility. As you can set the voltage, the angle, the impedance, etc. So this is the way to control the Autostep. Now, what else? If we go to the to see what happens, these are the voltage and current generated during the swing. So we have a pre-fall time, and then we have a swing for the voltage and a swing for the current. And here it's not actually, it's not the actual trip time of the rate. This is simulated, but we did some tests on some protection. So, but it's nice to see where the characteristic, where the impedance locus is moving across the characteristic of the relay. So, a real test on the relay here this was a test on a Siemens relay, Siemens 7SA5 something, and this is a simulation of a power Autostep. Sorry, I also get confused between power swing and Autostep. So this is what we expect to inject in the relay, okay? And this is what a SIGRA, which is the Siemens software. We could have done the same with any other relay, but at that time when we did this test, this simulation, we only had this Siemens relay, and then but same thing happens with ABB, with Cell, with Alstom, with the GE, etc. So any protection does the same. So don't consider this as the promotion for for Siemens. So the impedance seen by the relay is what you see here, which is basically more or less what you see. What you see here, you see the impedance, the maximum impedance is about 120, and if we look at this line here, it goes down to the second, and this is 100, and this is 150. So we are what we simulate, what we think we are generating is exactly what the relay is seeing. So this is the impedance. I mean the zoom, and this is the zoom also in the contract file and the simulation. Sorry, the representation in of the impedance locus in the with software signal. Now, for the power swing, there is a bit different, because we cannot apply in our system the superposition of the effect, because we don't really know exactly how the swing is moving unless we do a simulation with a frequency change, frequency range. Now, this is also possible, but it's very complicated. What we do with this model for the power swing is that we always have this characteristic, but we give the user the possibility of selecting his own impedance path by clicking on the graph. So you can click here, 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 etc., and you define this impedance graph. And this is what, if you remember, this is the stable power swing. That means the impedance goes in and out, but it doesn't go out from the other side. So it is recovering the position. This module, you can fix the speed at a certain ohms per second, and this will generate 89 steps in our state sequences simulation. Every step is lasting 10 milliseconds. Is this possible? Yes. Can we do this? Can you do less time and make a very smooth change? Yes, we can. But in this case, we'll limit the duration of the swing because we have a limit in the number of states that we can simulate in one state sequence. 18, we can go up to 100. So here you can also apply after the last swing. You can simulate a fault, so you can change this type of test from swing to load and to fault. So in general, you can get to the impedance characteristic as per the relay setting, as you remember, with the COF. Superimposed impedance locus, so we can show the impedance locus on the graph, and we can set the impedance locus point by point, the type of point, whether it is a swing or a fault. Up to 4 timers we can monitor for trip and block signal, and then we can set the speed in ohms per second. So if we click on this checkbox, then we can fix the speed of the swing in at one specific value, 100 ohms per second, which is quite important because it is related to the setting of the relay. Remember that delta time also defines a speed in ohms per second. Now, can we do, what is the simulation that we can do? So suppose that we simulate this, then this is what the relay is measuring. So after the simulation, the relay is measuring exactly the same stuff that we are simulating here. And now forget about this initial part because it is related to the way the impedance is measured by the relay. The relay is measuring the impedance using the fast Fourier transformer. So this is to determine the fundamental in a very short time. But of course, at the beginning of this record, it only has one sample and then a second sample and a third sample until it completes a cycle, let's say 20 milliseconds, and it's got all the information to determine what the voltage and what the phase angle is for that particular voltage. So at the beginning, it doesn't have the full information, and then it draws this all this stuff here, which is not important for the relay, because the relay, this is just the record. Okay, so this is what is simulated by the software, and this is what is measured by the relay. So, and this is the end of my presentation. So we have seen how we treat the two methods, the two phenomena, power swing and Autostep. So to conclude the power swing, we're using sort of state frequency, but it's very smooth, so that the relay, so we hope the relay doesn't see the fact that the impedance is generated with steps. Not it's not exactly a smooth change of the impedance. And for the Autostep, that is a real swing due to the difference in the frequency of the two systems. Now, if you have any questions, then,
thank you very much, Mauro.
You're very welcome to.
For the very quite really entertaining and nice presentation. We have quite the questions actually. So let me begin right away with these questions. The first question is that when do we have out of a step, and when do we have power swing in relay protections? Just quickly.
Okay, so close this. In the stuff. So in Autostep is when we have seen it's when we have two systems with impedance. So the source impedance, this is line impedance, and here we have the remote and the generator. So this is ER and this ES. So the power swing is when you have let's say a fault somewhere here, and it is cleared very quickly. Then in this system, the
Mauro,
yes.
it seems that you are on pause for your screen.
Sorry?
Or your screen is not showing, I believe, or you are on pause maybe
showing.
again.
It's not showing.
Yep.
Sure.
Maybe try to share it again,
okay.
or you are already sharing the presentation maybe, or the window for the presentation.
Okay. So this is the drawing that I was doing before. Can you see it?
Yes,
that?
it's clear now.
Okay, perfect. So when you have a power swing, when the fault is cleared very quickly, and then the relay doesn't. If this is the characteristic of the relay, the system doesn't go into the instability mode, right? And this is for line impedance. You have a Autostep when the fault is not clear in time, and then the and then the system goes inside here, so the impedance goes inside here, and then it starts losing the synchronism with the rest of the system, and then it goes out, right? So this is what happens in for the range.
Right.
Yeah.
Another questions that we have quite a few, to be honest with you, and maybe we are a little bit short on time.
Okay.
Why are you changing the way you test power swing and out of a step?
Yes, because of this basically, and because here we can see in our previous tool, we don't show the impedance locus and we don't show the characteristic of the relay. And we have a voltage and current showing in the same graph, and sometimes they are not very visible. So voltage and current are displayed separately, which is the normal way. And then, of course, it's extremely important to see the impedance locus on the graph here directly, like this. Okay. So we know where the impedance locus is running, and something that we don't have with the previous tool that we have. So it is we've been requested to have this feature so much that we had to do it.
So basically, it's an improvement that been requested many times.
It is an improvement which has been asked too much, and that at some point we have to take action.
We have rather than a question, it's more of a request. Someone is asking, how can we have the power swing module?
The power swing module?
Yes, this one.
That's a request. That's very good question. This, so at this moment, this will be available on all the templates that we are creating for the different protection for the cell, for Alstom, for GE, ABB, etc. So we will add the power swing and Autostep module, and then in one of the next version we will make this available for everyone to pick from the test picker. So if we go to our software, basically it will be available. Can you see my screen, right?
Yes.
It will be available. So in this position where we see power swing, so this will lead to a different page, something that which is basically what I've shown you before, or something very similar. We might need to adapt to the to a new format, right? So this one is leading to this, and as you see, it's not exactly what people is expecting to see for power.
All right. With the last question that we have, or what time allows to have actually, what is the disadvantage of this method, and will it work with all relays?
Well, good question, because we to make sure that it works with all relays, we have to test with all relays. So it is just a matter of keep testing and testing and testing. In general, for the Autostep, that is a method that always works. For the power swing, which is based on state sequencer, although it is very fast state sequencer, I can show you the what is it? Power swing. This is the okay. This I don't remember what, but anyway, can you see my screen, right?
Yes, we can.
So I can say to a certain number of points. As you see, that I have 52 steps, and I have defined as a minimum time for each state 10 milliseconds. And if I go to the test, so if you see here the impedance at every step, for every step the impedance change a little bit, and voltage and current are changing. But this is, of course, and the time is 10 milliseconds. It's very short time, so it's a half a cycle at 50 hertz. So slightly more at 60. I'm not really sure if I have selected the time based on the nominal frequency. Make sure that I have half a cycle every time. So so this method might not work for our relays, and in that case, we might need to tune up this testing for that particular relay. In general, for the experience that I have, this method is working because the delta time for each state is very, very short.
Okay. So we still have some questions maybe, but unfortunately we are out of time. We have another session by
Yep.
Dr. Danish Babu that will be starting very shortly. Thank you very much, Mauro, for this wonderful presentation. If anyone have any questions, please leave them and we will get back to you at a later time as well regarding this topic. So now switching to Dr. Danish Babu for his presentation on busbar differential testing. After that, we will have another Q&A session for that topic, and then maybe a small break for 5 to 10 minutes.
Okay. I will assign now the presentation to Mr. Dinesh Babu.
Yes.
Yes. Dinesh, if you're ready.
Just a moment, let me switch on my camera. Good morning, everybody. Thank you, Ali and Mauro. It was a wonderful session. Many new things to observe. I think the software features are somewhat new. Even I had a lot of new things to learn. Okay.
Thank you, Dinesh.
Yeah, am I audible and is my screen clearly
Yes.
visible, Ali?
We can hear you clearly and see the screen clearly as well.
Okay, thank you.
Okay.
Okay, so let me proceed. Here we are going to see the busbar protection implementation and testing challenges, which we have seen for the past 10 years. We have been working in this area with customers. So what we are presenting here is actually the experience which we gained during the time of testing busbar. Several concepts and logics which we have been implementing in the field had some issues after some time because the theory that we design is not 100%, it may be 99%. So during real field issues, we identified how well we can fine-tune this logic, and then we kept on making things better and better. So at this point of time, we feel that this is something which is maybe 99% good, since these logics are implemented in the field, and it is in service without any issues for more than 5 years. So it's actually a summary of a few papers which we have presented in international conferences and journals. So this is just a summary, around 6 conferences and few journals. So what we published is actually the concept which I am going to present here. The outline for this is as you see here. We talk about the busbar protection, the conventional engineering which we carry out, then the issues which normally we find. Because busbar is a very critical application. When it trips, it pulls out the entire substation and creates very big chaos to the user. But on the other hand, a bus fault is very rare. It happens maybe once or twice in a year, not like a distance or a feeder protection, which you can see a lot of faults happening regularly. If you take a distance, maybe 2-3 faults in a month, but busbar maybe 1 fault in a year. So even if we make some mistakes in a busbar relay logics, it's very hard to identify because the fault is rare. So the experience which we gain to fine tune a busbar logic requires more duration. So out of this, the application issues, we find that in the left hand side I have shown here, the bus unification, isolated discrepancy, the blocking logic, CT trouble, end fault, LBB, and CT trouble. These areas we find a lot of maloperations happening. So here we are going to suggest some logics which would help you to fine tune the existing logic. And here what I am going to present does not require you to buy a new relay or change something. What we are going to discuss is something which is already available in the numerical relays which you are already having. In case you are not having numerical relay, you can try to implement this kind of philosophy using the conventional schemes, using series parallel combinations of the electromechanical relays. And if you have numerical relays, of course, you can utilize the functionalities available inside. And even if you have a numerical relay, it need not have all the features in the enabled state. Normally, the default configuration is different. So unless we test it properly, enable the feature and implement it, we will not be able to utilize that functionality in the relay. So let me go ahead with the discussion. The protection fundamental. So here the fundamental does not change. We still talk about the most price scheme of differential protection in 2 areas, that is the low impedance and the high impedance type, with 2 types of architecture such as the centralized and the distributed type. So this is something which it will help you to understand some information about copperless busbar. So in the last line I have written copperless busbar. Currently we talk about IEC 61850 9-2 standard. So where we try to eliminate the copper cable even in the switchyard and try to use optical CTs and PTs to eliminate the copper. So here what I am trying to share is a solution which we have already implemented widely in India in many substations for busbar. So that needs a clear understanding on the centralized and distributed type of architecture. The next one is additional security. So this is very, very important. This is some numerical relay specific point of view. Directional principle and rate of change of restraint algorithm. This is very, very important, and it is available in numerical relays, but unless we enable it, this function will not be implemented. So this is something which you can test and verify to check if it is already available or not. Or if you are the end user, you can also think of fine-tuning your specification to get these things implemented for the future technology. Okay, so here we talk about these kind of principles. This is the dual slope characteristics, slope 1, slope 2, which we know slope 1 which normally acts for the full load current, and beyond that when the CT gets saturated we move to the slope 2 characteristics, and then we have the operate and the block. So when the differential current is read above the curve, the relay reads differential current. Above the curve, it trips. If it is below the curve, it blocks. So the region becomes big as we give more area for the errors in the CT. So during the CT saturation condition, the error would be more. So that time, even if the differential current is available here, the relay would not trip. However, we have some challenges here. The slope to normally we configure between 75 to 89%. Normally 90 is not recommended, but 75 to 60%, 75%, 80%, like this, if you calculate as per the standard, you get some value. So let us say if it is 72%, let us say you have configured slope to as 72%. I can say if my differential current is below 72%, it will block, and above 72%, it is going to trip. So it's okay when it is away from the line, but if it is at the boundary, you may have some kind of chattering effect, or the misbehavior of the relay is not, the proper operation is not guaranteed. So how do you define 72? Why do you conclude it is 72? Why not 72.5? Why not 71.5? So this the values that we enter is actually not always 100% perfect. It's prone to human error during calculation, and also during the time of calculation, we assume a lot of parameters from the nameplate details, which may not be true after a few years because of the aging and the wear and tear of the equipments. Then the settings also has to be updated, which normally does not happen. Whatever settings that you have during the time of commissioning is going to continue for the next 5 or 10 years as long as the relay is in service, unless you add some feeders or do some kind of busbar augmentation. So the intelligent electronic device comes with this kind of additional security. So here what we are telling is, forget about 72, 71.5 or 72.5. Let us make some mistakes, even if the value is wrong. What we want to know is, if I measure the differential current above the curve, I should not trip if it is not a fault. If I measure below the curve, I should trip if it is a fault. This is the concept which we are talking about. This is the security which we are discussing. So it should not just be dependent on one specific parameter. There should be multiple parameters available in the relays to ensure that man-made mistakes or adaptive protection is possible. So that's where you can see the directional principle. So what is directional principle? The directional principle states that when a fault occurs, all the current should flow towards the fault. So the angle between the currents should be less than 90 degrees. That's what we show here. So the operate region is all currents will be having the same angle. If it is any one or multiple currents are outside, that is more than 90 degree, then the relay will not operate, thinking that the differential current is because of some error. So this is called as the directional principle. And we also have the rate of change of restraint. So the rate of change of restraint is like not only the differential, even the restraint current has to increase. Okay. So for example, let us say I have two CTs, left hand one CT, right hand one CT. My incoming current should be equal to my outgoing current. And let us say I remove the cable in the CT secondary. This is not a fault, it's a mistake in the CT secondary. Now, because I removed the wire from the relay in the CT secondary, what happens? The relay reads differential current, but there is no fault. So how do you differentiate this? So the relay knows this. How the relay differentiates this? If you remove the wire, only the differential current will increase. Restraint current will not increase. But if there is a fault, your restraint current also will increase along with the differential current. So this principle is called as rate of change of restraint. So the relay does not just monitor the differential current alone. It also monitors the restraint current. That's what we also see in this particular parameter, where the differential is in the y-axis and the restraint is also in the x-axis. So as you increase your load current or the fault current, we move away towards the right hand side of the x-axis. So more details for clarity, let's move on. we can take this as a case study for our discussion here. 2 bus bar. Normally, it's good to discuss on 2 bus bar or 3 bus bar because that has a complicated scheme selection logic. If in single bus bar 1.5, you don't have much bus bar logics. So here you can just analyze this. We call this as bus 1. We call this as bus 2. We have 3 bays just for our understanding. One is an incoming, the generator feeding the bus, and it is going to come out through one bus coupler. You can see the status. So green means open, red means close, and we see the bigger box, bigger rectangle is the circuit breaker, and the smaller rectangle is the isolator. So how do we understand the zone selection logic? So here what we do is we create a chart like this. In this chart, we allot the CTs. So we call this CT as one CT, first bay CT, second CT, third CT. Each CT will be allotted to each zone. And we also have something called as the check zone. The check zone is for additional security. We will see what is the use of check zone here. The bus coupler or a bus transfer bay will never read in the check zone. All other bays will always read in the check zone, irrespective of the isolator status. The 1 CT and the 3 CT, which is not a bus coupler and a TBC, these will read in the respective zone only when the isolator is closed. Respective isolator is closed. For example, currently all are green, so they are not reading here. So if it reads, you will find that 0 value here. If it is not reading, it will be blank. So when we move further, you will understand what I am trying to explain in this figure. Let's close some isolators and see what will happen. So now we are going to feed like this. The generator feeding bus 1. From here, it goes out, line 1. Bus coupler is open, both bays not connected to zone 2. So now, what is the CT selection logic? Since 89A isolator is closed, this reads in zone 1, N1 also reads in zone 1. So 1 CT in zone 1, 3 CT in zone 1. Both are here. Check zone, irrespective of isolator, it will read. 2 CT, no current is there and isolator is open, so it will not read. Check zone, it will always not read. Okay, now let's see the current direction. Current flows inside, flows outside. So we assume a convention that the CT earthing should always be towards the protected equipment. So here the current flows towards the bus. Assume that towards the bus means 0 degree. That is the earthing towards the bus bar. Electrically, it is earthing towards bus bar. Mathematically, you can assume that it is 0 degree. It need not be 0. It can be 180. It can be any assumption. But whatever you assume, you have to assume uniformly throughout the example. So here my assumption is whenever current flows inside the bus, towards the bus, it is 0. So away from bus, it is 180. If your assumption is 180 for towards bus, then away from bus would be 0 degree. So with this assumption, we can see the current here, 1 angle 0, entering to bus 1, 1 angle 180, going out. So when you add this vector addition, differential current is 0. And for our example, let us say maximum current principle. So that destined current is, which is maximum, that is 1 amps. So maximum is 1. So when we plot this, it would be below the curve. The relay does not operate. Perfectly balanced system. Moving further, bus bar 2. Okay, now I am going to feed through second bus like this. So let's see the allocation. Check zone always reads. Bus coupler will not read in check zone. Since 89B is closed, both feeders are reading in zone 2. Same current direction. Therefore, 1 angle 0, 1 angle 180. System is perfectly balanced. Third example, through the bus coupler. So we are feeding to bus 1 to bus 2. Bus 2, it flows out like this. So let's see the current allocation. So 1 CT, let's go one by one. First of all, let's see check zone. Check zone, bus coupler will not read. 1 CT, will read, 3CT will read. So these two are available here. We will discuss about the angle later. So first of all, it is reading here. That's all. Next is here. 189, A is closed here, B is closed here. So whenever A is closed, it will read in zone 1. Whenever B is closed, it will read in zone 2. For bus coupler, both A and B are closed. Therefore, it will read in both zones like this. Now let's see the angle. The CT earthing towards the bus, this we discussed. So when one CT is earthed towards bus 1, towards bus 2 CT. Now you have two options. Either you earth it towards bus 1 or you earth it away from bus 1 or towards bus 2. Both are same. When we do that, what happens? Let us assume that CT2 is earthed towards bus 1. What happens? One angle 0, this goes out. One angle 180. This also goes out. One angle 180. So now we have to see this independently for bus 1 and bus 2. Now this CT goes inside bus 1, comes outside bus 1. So for bus 1, it is incoming and outgoing. 0, 180. This is CT is earthed towards zone 1. That means it is earthed away from zone 1. If it is earthed away from zone 1, incoming would be 180 degree. So 2CT, which is reading 180 here, would just add by another 180 here. Okay, the outgoing of bus 1 is actually the incoming of bus 2. Therefore, the angle changes here. The same current, but the angle changes. This normally happens in the numerical relay configuration. If you are using a electromechanical or a high impedance scheme, we would use two different cores, where one core would be earthed towards bus 1 and other core would be earthed towards bus 2, and this confusion would not be there. But in low impedance relay, we need not use two core. Inside the relay, you can just add 180 degree in the configuration. Therefore, this kind of adjustment would internally happen. So our concept is very simple. Always incoming and outgoing. At the same time, the earthing has to be constant. If the earthing is towards bus, then incoming is 0, outgoing is 180. If the earthing is away from bus, then the angle would be totally reversed. So from here, what we see here, 3CT, which is 3CT, this one, it will read in bus 2, zone 2. So from here, what you see in this chart, 1 angle 0, 1 angle 180, 0, 1 angle 0, 1 angle 180, 0. So this system is perfectly balanced. This is the concept for dual zone operation through bus coupler. The same thing holds good for 3-bus operation if you have a TBC, transfer bus coupler. Now, let's see the issues. So first issue, application issue, bus unification. What is bus unification? See, when accidentally we close two isolators like this, we may think that this is not possible, because in the scheme we will create an interlock such that you cannot close 89B when A is closed. But we always design the protection system for worst case scenarios. So let's say the worst case scenario, your interlock failed and both are closed. When both are closed, what logic we usually use is we eliminate bus coupler CT. This CT has to be removed from your entire bus bar differential calculation. Why do we do that? We do this because when you close these two, this is actually acting like a parallel path. So the current will flow from here as well as here. So that means it may be 50-50 or 49-51, depends on the resistance of the path. So you will have a parallel path. When you have a parallel path, the current that you read in this CT is not the correct current, it is wrong, because there is some amount of current flowing in this path which is not read here. Therefore, what we do is we will never account a wrong CT. We will eliminate this bus coupler. So when you eliminate this, what happens? 2CT will not read in any of the zone. So this is logic number 1. Second logic, we will read all the CT in all the zones. If any one bay has both 89A and 89B closed, we will read all the CT in all the zones. That's all. So now how many CTs are there? Even if you have 24 bays or 50 bays, When one bay 89A and B is closed, all the bays will read in all the zones. So you will have a logic mix. Now you can see the system is balanced. One angle 0, one angle 90. Differential is 0, 0, 0. No fault. Now the question is, what happens when a fault occurs? Fault occurs in zone 1. Okay. When a zone 1 fault occurs, all the CT will read in both zone 2 as well. That means the relay will trip zone 2 as well. So we are not having any zone segregation here. It is treated as a single zone. And that is how it has to be, because these two are isolators. Anyway, there are no two zones once you close these two. If there is a fault in bus 1, there is no point in opening this bus coupler, because the fault will still be fed through this path. Therefore, it is treated as a single bus. And in this kind of zone allocation, we are treating it as a single bus. So wherever the fault is, zone 1 fault or zone 2 fault, we will trip the entire bus bar, because the operation philosophy is in that manner. So for bus unification, the logic that we use is two logics. First logic, remove bus coupler CT. Second logic, read all the CT in all the zones. That's all. This will perfectly work for this kind of application. The first issue and the solution for this issue. Now moving on to the second issue, isolator discrepancy. An example. So we already saw this example. Generator feeding bus 1. From here goes to bus 2. From here comes to bus 3. The system is perfect. Like this, we are able to see this. Now, isolator discrepancy means any one of the isolator, physically it is closed. Okay, physically it is working fine, but it is not giving the input to the relay properly. For example, 189A, you can closely observe this red color. It is now white in color. I don't know. This is discrepancy. So the relay does not know whether it is an open or closed, but physically it is closed. That means physically current is flowing, but the information is not coming to the relay, because finally this is going to be a contact, the 52A and 52B contact of the isolator, which would be wired to the binary input of the relay. Your contact can fail, your cable can fail, your input can fail. So anywhere a mistake can happen. Now what next? Let the mistake happens. We are designing it for the worst case scenario. When mistake happens, what next? When this isolator is missing, according to our logic, this current will not read. 1 CT will not read in zone 1. When this is not reading, differential current will be reading 1. Differential will become 1. So when this becomes 1, what will happen? Bus bar will trip in zone 1. Now how do you prevent this? Because it is not supposed to trip, it is not the fault. Isolator discrepancy is a secondary system problem. Your cable problem or input problem or relay problem or a isolator contact issue. For that you cannot trip the bus bar. So how to prevent this? But according to the Merce price scheme of differential principle, it will trip. So to prevent this, the additional security which we spoke earlier, we have to create a security in this fashion. A 3-input AND gate. Main zone, MZ stands for main zone. It has to be directional always. Check zone should always be non-directional. Check zone should never be directional. If you create a directional check zone, it will maloperate when your system is working on 2-zone concepts. Third, bus PT supervision. This is a beautiful concept which can be implemented. So supervise the voltage of your bus bar. Normally for differential protection, people never monitor the bus PT voltage. So this is very useful. In the forthcoming sections, we will also show you. And it's not a theoretical proposal. This is an implemented solution. It's working very well. So when all the three are satisfied, only then the bus bar will trip. Now let's see the same concept here. This trip logic. Let's see the above example. Discrepancy. 89A not reading. Current is not there. Differential current is reading some value. Now main zone differential. This will pick up. Check zone. It will not pick up, because this current is not dependent on isolator status. So even if isolator is not available, check zone will not permit tripping. Sometimes check zone may also maloperate. That time bus PT also will provide as additional security. So when is that sometime that check zone may maloperate? That we will see in the upcoming sections. So currently we are seeing isolated discrepancy. This is how the logic works. So the problem is some isolators may give wrong information. Solution is we have to use this kind of additional secured logic to ensure perfect tripping. Third type of issue, busbar blocking. So this is normally whatever trip logic you use, we normally use a TNC switch, maybe from SCADA switch or from the busbar panel. We try to block the busbar. So how do we block it? We will have a contact input in the relay. That input will be wired to block the busbar. So whenever you throw the switch in the TNC switch from in to out position or in service to block position, this would become high. This would become 1. This would become 1. When this becomes 1, it is inverted and this becomes 0. So even when the relay has some problem, busbar differential is red, output will still be 0. So in this logic, what we understand here is this 1 is actually blocking busbar, and this 1 is actually a binary input which becomes high. Now the very interesting fact is theoretically you can see it seems to be a foolproof method. When I am testing a busbar, normally what I do is we will block the busbar, turn the switch to in position, and we start injecting some kind of differential current, and we are testing the busbar by isolating the tripping, all these things. We will do some kind of problem, and this can be blocking can be for zone 1 separately, zone 2 separately. So we can shift all the base to zone 1 and we can block zone 2 and test zone 2 alone. So this kind of testing philosophies people normally do. So in one such substation, a 400 kV substation, busbar testing, we blocked the busbar and we were creating a zone 1 fault, and the relay was behaving properly, tripping as per expected, not tripping as per our expectation. So relay testing was going on, but the busbar was in service. Zone 2 was in service. Now we faced an issue. There was a DC problem, DC interruption. The relay rebooted. The moment the relay rebooted, a busbar tripped. Now this made us to look why this happened, and then we understood that this kind of blocking logic is not the right way to do it, because for 99% of the cases it will work, but when a scenario which I just explained, when you are blocking the busbar and you are doing a busbar testing, during that time if the relay reboots, relay can reboot many times. Even if you write a 61850 boost signal, you have to reboot the relay to implement something. So if you say you block the busbar, do some testing, that time you change the goose information and you reboot the relay. Now what happens? The relay will trip. And why it trips? Because this input became high, and after it becomes high, it is going to not get itself and it is going to block. But this is protection logic which is far superior or faster than the binary input. Binary input has a sensing time of 4 to 5 milliseconds depending on the relays. So before the binary input senses and sends the blocking command, the relay's internal algorithm executes the tripping command. So this is the dangerous scenario which resulted in a maloperation. Then what we decided was we just made a small change. Same logic. Okay, it cannot be seen from here, but what we did was invert the binary inputs logic. That is, block the busbar whenever the binary input is low, not high. That's all. Very small change. It's a minute change in your engineering. So the difference between the previous logic and the new logic. Previous logic, whenever the binary input is high, block busbar. New logic, whenever the binary input is low, block busbar. So in this case, what happens? Even when the relay reboots, the sensing time is eliminated because it is already in 0 condition. So this will become 1 when the input is low, but when the input is high, this will always be 0. Therefore, you will be able to block the busbar perfectly even for that specific rare case scenario. So always let's understand this particular logic which I was trying to share. Busbar block always use a binary input low signal for blocking and not a high signal for blocking. That's the conclusion. Next is CT requirement. Okay, this is another debatable question, such as how many CTs should I use in a bus bar? 1 CT, 2 CT, or if it is 1 CT, where should I place the CT? So for this, let's see the analysis. Let's analyze this. We take 2 zones, a bus coupler. There can be left side any number of bays, right side any number of bays. Let's forget about the number of bays. We are looking at only the bus coupler. So first we will have 2 CT concepts, CT here and CT here, and we always go for the zone overlap to ensure 100% prevention of blind spot. So this CT is connected to zone 2, blue area. This CT is connected to zone 1, green area, and this is called as the overlap region, CT overlap region. So now let's see 4 faults: fault in location A, fault in location B, fault in location C, and fault in location D. And let's analyze what is going to happen in each location. Zone 1, zone 2. Location A, there is a fault. Only zone 1 will trip. Zone 2 will not trip. No trip. Agreed? That's how the CT is located. Fault is in the green area. So green means only zone 1. Now, gray area. This is the gray area. Okay, the color is different. I am calling it as a gray area because it's a questionable area. So point B is located, a fault located between the CT and the bus coupler in B. Now what happens? This is located in both zone 1 and zone 2. That means both will trip. Same thing, fault occurs at point C, both zone will trip. Fault occurs at point D. This is in blue area. Blue means only zone 2. So zone 1 no trip, zone 2 trips. Conclusion. Unwanted tripping of the zones in 2 scenarios, like in B and C. See, if you don't look at the CT. For B, it is a zone 1 fault. Zone 2 should not trip. For C, it is a zone 2 fault. Zone 1 need not trip. Based on the CT location, we have tripped both. So we call this as unwanted tripping in 2 scenarios. It's the conclusion. Why should you trip unwantedly when there is no fault in my zone? This is the question. Yes, we tripped because there is no other option in the scheme. That is a different point. But the question here is, since there is no point, we tripped it. Is it really acceptable as per the protection philosophy? So let's see the other way of doing it. Only 1 CT. Now let's see the same chart. Fault at location A, green area, zone 1 trip, zone 2 no trip. Fault in location B. If this is an external fault for zone 1. So normally we create a logic for this. So what kind of logic? That is, for this is a zone 2 fault according to the CT for B. So when the fault occurs in B, zone 2 will trip, zone 2 tripped. When the breaker opens, this current is supposed to read 0 current. Sorry, the CT is supposed to read 0 current. If the CT is not reading 0 after the breaker is open, zone 1 will trip. Therefore, there is a delayed trip. So here also we find that zone 1 and zone 2 has tripped. Fault at point C, blue color area. Therefore, zone 1 no trip, zone 2 trip. Fault at point D, zone 1 no trip, zone 2 trip. So here also we find this chart. Very good. Now what we conclude? Unwanted trip of the zones only in one scenario, that is B. In B scenario, that is when the fault occurred at B, unwantedly I tripped zone 2. But there was a delayed trip also. Okay, so what is the difference between the 2 CT arrangement and 1 CT arrangement? Previous 2 CT arrangement, Ali, can you hear my voice? Am I audible?
Yes, Doctor.
Thank you, because I just saw a chat message which said no sound, so I just cross-checked. Thank you.
Okay, please carry on.
Okay, so in 2CT arrangement, we find unwanted trip in two scenarios. In 1CT arrangement, we find unwanted trip only in one scenario. However, there is a delayed trip in one scenario. So this is, understanding the pros and cons in both systems. So there is no specific recommendation telling that you have to use 2CT or you have to use 1CT. What we understand from here is you should not conclude that 2CT is the best or 1CT is the best. What we conclude is in 2CT, unwantedly we trip for two scenarios. In 1CT, we trip only for one scenario. So this is better. However, there is a delayed tripping. So when you are using this kind of system in a station where your fault current is low, or maybe in a TBC where only one bay is going to be connected, if you are going to be connecting only one bay to the bus bar, then why should we worry too much about the delay? Because when one bay is connected to your bus bar, and if there is a fault in that specific distance protection line or something, we wait for 40 milliseconds. That is the trip duration permitted for a distance protection. But if the same one bay is connected to a TBC feeder, and if a bus fault occurs in TBC, why do we say that we have to trip in 15 milliseconds? 15 milliseconds is the tripping time for a bus bar. So it all depends on, how many bays you are going to connect to the bus bar. So if you are talking about TBC, single CT, this kind of single CT arrangement is sufficient. But if you have a generation station bus bar where even every 1 millisecond is going to reduce the life of the equipment, then 2CT arrangement would be better. However, we have to understand that there would be a unwanted tripping during two scenarios. So that's about the CT requirements and the pros and cons. So we don't conclude anything, we just understand both options. Next is end fault. Okay, end fault or blind spot detection. So normally we say when the fault is between CT and the breaker, we trip the remote end. So this should not be a blind definition. We have to look at the single line diagram. So let's see in this example, you have a bus bar, you have a breaker, and you have a CT, and this is connected to the remote substation where you have another bus bar and a CT. Now, a fault occurs between the CT and the breaker. Location is here. Now, this CT has two kinds of protections. One is the distance protection, which is looking at this direction in the forward. The bus bar, which is looking at this direction, which is in the reverse direction. Now, distance protection will not clear this fault because it is in the back side. So it is a reverse zone, zone 4 or zone 5, reverse zone operation, which is having huge time delay. But bus bar will trip this breaker because it is within the CT and the breaker will open. Now, when the breaker opens, the bus bar will not feed this fault. However, the remote line will still feed the fault because distance protection has not issued a trip command to this breaker because it did not detect the fault in zone 1. And this relay, another distance relay available in the remote end of this line, this relay will not see this fault in zone 1 if it is an underreaching scheme because it is in the last end zone section beyond 80%. Therefore, this breaker will open only after zone 2 time delay, that is maybe 200 or 250 milliseconds depending on your utility standard. Now, after knowing there is a fault, why should you wait for 200 milliseconds? Therefore, what we do is, when the bus bar relay trips the breaker, when the bus trips, it will monitor the current. That is, when the breaker is open, overcurrent will be enabled. Simple. You can say we are just using overcurrent, but the overcurrent will be blocked when there is a breaker is closed. Overcurrent will be enabled when the breaker is open. So when the breaker is open, overcurrent will be enabled. After a timer, maybe 150 or 200 milliseconds, not after a timer. When the breaker is open and if there is current, there is no time delay. Immediately, instantaneously, it will send a remote trip. This is called as DT. This overcurrent is also optional. So in some stages, what we do is we normally send a direct trip DT, even without monitoring the current. That is also possible. That option can also be used because anyway, this would be a floating line. But in some utilities, people don't use a floating line. They would like, some utilities like the line to be floating. Some utilities do not want a floating line. So there are two concepts because some people feel that if there is no sound on the overhead line, people will climb and cut the jumper. Lot of copper theft is going on in many places. So for that, the utility will never allow a de-energized line. So when people hear the sound, people normally don't climb the overhead line. They risk the life to do this kind of theft operation. So the utility standard is always keep the line energized, even if one side breaker is open. So that kind of scenario, they use a overcurrent, but without overcurrent, when bus trips, you can trip the remote end. This is DT, direct trip. This is one concept. So this concept is true only when the CT is after the breaker from the bus. So the line, bus bar, followed by breaker, followed by CT. In this kind of situation, this is true. The other scenario 2. Here you can see the breaker and the CT is swapped. Bus bar, followed by CT, followed by breaker. This is the order of your equipments. So in many places, you may find like this also. So in this kind of scenario, what happens if your fault occurs between the CT and the breaker, same location fault? So here what happens? Distance protection will actually trip the breaker because it is in zone 1 forward direction. And it will also send the carrier to the other end. Carrier will see this as zone 2. So both ends the line will trip. However, the fault is still fed from the bus bar. Because we opened the breaker, remote end will not feed, but the bus bar is going to feed the fault. And this fault is an external fault for the bus bar because fault outside the CT. So how do we trip the bus bar? So here, same logic, same overcurrent. Whenever the breaker is open, monitor the current in the CT. If there is current in the CT, trip the bus bar. So this is the additional logic which we need to implement in this kind of scenarios. So normally this is a very rare scenario. So even if you have not implemented, you might not have come across this real-time issue. But this is the perfect method to ensure that even for the worst case scenario, the bus bar is going to trip properly. If this is not implemented, then of course after 200 milliseconds LVB would operate, but there is a time delay. 200 milliseconds for the bus fault, known bus fault, is not advisable. So that's about remote end tripping or bus bar tripping. Which end should you trip? This depends purely based on the location of your CT and the breaker, and it is not just based on the definition that when a fault occurs between CT and the breaker. It depends on where it is located. Okay, the solution is here. So this is the problem with the end fault, and now we are going to see LBB, local breaker backup. So breaker failure initiation has resulted in several unwanted tripping in bus bar. This is very common, and this breaker failure initiation can occur due to spikes in the cable. So how can we solve this? Solution: always make the breaker fail initiation signal as self reset and do not latch it. If you latch it, what happens? If you talk about spike will normally be less than 10 or 15 milliseconds maximum. Less than 10 milliseconds. Spike means input becoming high and becomes low. And this duration between the high and low would be around 4 to 5 milliseconds. This you can always find it in the event record of the relay. So when you analyze the event record, we can find that it's a spike. But whenever the spike occurs, it energizes a binary input in a relay. That input will hold. After 200 milliseconds, when the current is superposition current is there in the CT, LBB will operate. So during healthy condition, current superposition current will always be there because it is a loaded line. So whenever the current is there, if you monitor the binary input and if you latch it, LBB will misbehave. So to prevent that, only one small logic you have to change in the relay. Make your breaker fail initiation signal as self-reset, number one. Second option, suppose you feel that this is risky because maybe some other scheme is interlinked. Then what you do, you have to implement retripping. Retripping is not for the bus bar, it is only for the respective bay. So if there is a initiation signal in a specific bay, trip that particular bay, don't trip the entire bus, and you do that within 100 milliseconds. In 100 milliseconds you have to clear the fault. If it is not clearing, then you go for the LBB in 200 milliseconds. So this is the second solution. You can choose whichever is applicable. The third solution, implementing debounce timer. So in numerical relay we have a timer called as the debounce. Debounce means even when the input becomes high, when the voltage is high, the binary input will not become high till the timer is exceeded. For example, if you see in the many numerical relays, you have the debounce timer in the contact input. So let us say the debounce is configured for 10 milliseconds. Then even if you make the voltage signal high, only after 10 milliseconds, the input will become high. So in this way, unwanted debounce, unwanted spikes can be eliminated. Even if there is a spike signal, it will come down in less than 10 milliseconds. However, you may ask a question, how can you define that spike can be 10 milliseconds? It can be 11 milliseconds also. So that is the drawback of this method. So if you have that kind of issues, we have to go for first option or second option. So a combination of these things has to be implemented to ensure this kind of issues. Okay. Now, this is a good point. Normally, the specification says that LBB should be 200 milliseconds. If you configure debounce timer or as 10 milliseconds, then after 10 milliseconds only the input will become high. That means I am increasing my LBB time from 200 to 210 milliseconds. So what we suggest is you reduce your LBB time to 190 milliseconds because the balance 10 milliseconds is compensated in the debounce timer settings. So finally, as per your specification, your trip time would be 200 milliseconds. But internally, you are doing some kind of detection logics here. Okay, next. CT trouble. Okay, CT saturation detection. Here we initially started with a discussion about this line. This can be, like 69 or 72 or 75. Even when 1 degree changes, there may be a different behavior of the relay. So for that, we have a CT saturation algorithm detection. This you have to test it during the time of testing, because if you have not enabled it, it may be in the relay, it is there, but it is not in service. So what is CT saturation detection? This is the differential current. This is the restraint current. This is slope 1. This is the minimum current for differential beyond which the relay would trip. This is breakpoint 1. This is breakpoint 2. This is slope 1. This is slope 2. So you know the fundamental behind all these things. Now the CT saturation detection. Let's see the fault in 3 stages. Healthy, fault, after the fault CT saturates. Because there is a difference between fault and CT saturation. CT cannot saturate instantaneously. It is actually a mechanical equipment, right? Ion which is becoming a magnet, energizing, de-energizing. So there is some time delay between that. So there are 3 stages: healthy state, fault state, CT saturation state. So with this 3 stage, we are going to see during healthy state, the relay reaches the differential current here in point A. Now, when a fault occurs, what happens? Slowly the current increases. Slowly means I'm talking in terms of nanoseconds. Just differentiate and try to understand. We are taking a zoomed view. Okay, so I am going to create a 10 milliseconds as a 1 minute window. So when I see like this, when a fault healthy state, fault occurred, slowly my current increases. That means what? My restraint current increases, my differential current also would increase. So after some time, I would plot here in this point B. From A to B, in nanoseconds it has moved. After it reached B, the CT got saturated. Now, since the CT gets saturated, what happens when CT gets saturated? It will not read more current. It will read the same current beyond that. So one CT will read the same current, other CT will increase because all the CTs are not getting saturated simultaneously. So now, because of one CT saturation, differential current will increase. Now you will read the point at C. So when the locus is A, B, C, it is CT saturation. Now let's see the other case. When there is no CT saturation, internal fault. Okay. Okay. Earlier, what I discussed was an external fault. Fault outside CT saturated. Now fault inside CT saturation. Now when a fault is inside, you can see the differential current will move from A to C. It will not move from A to B. Because whenever the current increases, differential current also increases, and it will directly cross. So the moment you cross this point, the minimum settings, I mean, the relay would trip. So before the CT saturates, the relay has already issued a trip command. So CT saturation for internal fault is actually not a question. When the relay trips, after that the CT would get saturated because of the breaker operation time. But for external fault only, we have to ensure that the relay does not trip, and that is using this locus theorem. The relay would be stable for external fault CT saturation conditions. Okay, I'm just moving since we have only 5 minutes left. The last part. Oh, okay, just an application example on the CT trouble. This CT gets a problem, CT trouble. What happens? Your zone 1 and check zone both are having an issue. So this is what I was talking earlier. Even your check zone would have problem because you are reading from the same CT. Then you will have differential current. That time, even your main zone and check zone may misbehave, but your bus PT would not misbehave. Okay, so centralized, this is the architecture, that is different CTs connected to the relay. Phase segregated, one phase for each relay, and distributed, this is the architecture, one relay in each bay, all the relays connected through fiber cable to the central unit. So this is called as the distributed architecture. So in CT trouble, we would implement the CT trouble logic in each and every relay. So the logic goes like this. CT trouble along with overcurrent. So whenever there is an overcurrent, you will block CT trouble. So what is CT trouble? When there is a minute differential current available in the relay, because of some kind of CT errors or a wire problem in the CT secondary, you will get a CT trouble issue. So that time you will not have under voltage, it is only a trouble condition in the CT. But if you block bus bar using CT trouble, then during a real fault also it may misbehave. So we have to unblock CT trouble using a logic. So that unblock is overcurrent dropout. So using overcurrent dropout, you can disable CT trouble also. So same logic for double bus arrangements like this. This is zone selection logic. Bus 1 CT trouble, bus 2 CT trouble. When anyone is having CT trouble, it comes into this OR gate. Here we check the breaker condition. If the breaker is closed and the overcurrent has to be in dropped out condition, only then this logic would be enabled. So last area is copperless substation. Yeah, this is 1.5 breaker. So in 1.5 breaker, you don't need this CT trouble zone selection logic. CT trouble logic alone would be there. So the last part, copperless substation. The CT trouble logic we have implemented in a few substations. It is in successful service since 2015. So that's what we conclude here. Yeah, the last part, copperless bus bar. Copperless bus bar means what we are trying to tell is we are connecting the isolators, copper cable to the relay in terms of isolators. So how many isolators are there? One bay you will have 89A 2 wires, 89B 2 wires, 89T transfer bus 2 wires. So 2, 4, 6 wires for one particular bay. So if you have 24 bays or 30 bay arrangements, 30 bays into so many cables. So you have a huge bunch of copper cable connected from the bay to the relay to give the isolator feedback. And later we find that the isolator also will misbehave, maloperation of isolators. And to ensure that it behaves properly, we are providing sophisticated logic. Now the question here is, when you are going to create some kind of logic after knowing that it is going to misbehave, why do you want to wire that? Why can't we eliminate that much copper and save a lot of money and implement the same additional security algorithm inside the relay? So that's what this is about. So what we did was, there was a CT selection logic included. So whenever you give a close command, either through push button or from SCADA or through a pulse, that information will go and automatically the CT will get selected. You may ask a question that the CT would get selected even before operation of the isolator. Yes, that is true. However, the CT will not read any current till the isolator is closed. You have to close the isolator and then the breaker. After that only the CT will read. So even if you close it earlier, there is no issue because the current is 0. So what will happen if the operator fails to press the button or some kind of issues within the station? So this kind of alarms will be created. Where any differential picked up and check zone is not picked up, you will get an alarm. So check zone is independent of wiring. Therefore, using this alarm, we can always ensure that your system is perfectly connected. Okay, so since we are running out of time, I will stop this from here. Of course, you can read this detailed thing about copperless busbar, or you can also, I am available now, you can type your questions in the chat window, though I would not be, we are not having another 1 minute time to have the question answer discussion. I would reply to all your questions in the chat window in parallel during the next session. If you still have questions, you can type it in the chat window. So the last slide is about this copperless busbar, the logics which we discussed. This has been also implemented in more than 28 substations. Since 2014, all the substations are in service. So this is also a proven technology. So if you have issues such as, a lot of copper providing expensive solution based on copper wiring, then you can just look into what kind of solutions we are discussing. So yeah, a summary of all the things that we discussed. That's it from my side. Thank you.
Thank you very much, Dr. Danish. It was a very informative session, really. I learned a lot myself. It seems that we have a low count of questions, but we will take few very quickly, and then we will have a quick break for 10 minutes until the next session, since we have 2 sessions exactly behind each other, back to back, without any break. People to refresh, start to fresh again after maybe 10 minutes. While we are having that break, I will ask the 2 questions that have been asked here. The first one, it seems rather than a question, it is more of a comment or statement. Current IED, I'm reading it exactly as it is. Current IED won't trip that much faster from reboot. Relay rebooting time is more. Would you rather give a comment on that, Doctor, please?
Can you read the question again?
Current IED won't trip that much fast from reboot. Relay rebooting time is more.
Okay. See, what I am telling you is we are not discussing about the reboot time of the relay. After the reboot of the relay, once you have a ready LED which glows and which confirms that the protection is in service. So when the relay reboots, maybe some relays take 30 seconds, some relays take 5 seconds, some relays take 1 minute. We are not talking about how much time the relay takes to reboot, but after successful rebooting, it implements the algorithm for execution. So in that, what happens is there are 2 types of algorithms. One is the internal algorithm, the other is the external user program, the flex logic algorithm or the PSL algorithm which we create. These 2 work in integration, and then it throws the final trip output command. So when the relay reboots successfully, the relay is ready for operation. That time, before the binary input senses the external signal, because the sensing time is 4 milliseconds as per the relay specification. Before it senses and executes this command, because the external command execution also has a time delay, which is manufacturer specific, which you would not find in the manual. Some relays may take 5 milliseconds, some relays may take 2 milliseconds. Yep.
Can you hear me?
Yes, I can hear.
Yes, it seems that we lost you for a very short duration. Please carry on.
Okay, so let me repeat. We are not talking about the duration of the reboot of the relay. Some relay may reboot for maybe 10 seconds, some relay 30 seconds, some relay 1 minute. We are not talking about how much time the relay takes to reboot. We are talking about after successful rebooting, the relay has to be ready for the protection algorithm. So how the relay works is, it takes the internal algorithm, it takes the man-made external algorithm, and this external algorithm depends on several binary inputs which is configured. Now there is a duration for sensing of this binary input, there is a duration for sensing of this algorithm, that is external algorithm, whereas internal algorithm is very fast. So a combination of all these three is going to do a trip output command, and if there is an AND gate, it will prevent. But if it is inverted, like as I showed you, before the binary input senses, your internal algorithm trips the bus bar. So
okay.
maybe
Thank
your
you for,
release even after reboot it is working fine, but we have to test it and confirm. We cannot theoretically confirm.
We have another question we will be taking as well. It's rather than normal questions, it's kind of loaded question. The question states that I have an experience on MyCom B746M bus protection relay. It has function one box and it has a function 1 box and 3 box. If you choose the 1 box, you can use 1 relay. If you select the 3 box, you can use 3 B746M relays. Question is, if I will use the 3 box, how will the setup be of the protection? What will be the CT setup on that, and also how the tripping will work?
Okay. See, this is more into the architecture of the relay. So there are 2 architectures as we discussed earlier, centralized and distributed. In centralized, you have 3 boxes, R phase, Y phase, and the blue one. So in R phase, we connect all the CTs of the R phase from your system to this box. Y phase, all the Y phase CTs to this box, and D phase to this box. And each box would be capable of accommodating around 20 to 24 or 28 number of CTs inside this. This is the capability of the centralized relay. Whereas if you go for distributed, it can accommodate even more than 40 or 50. So centralized can accommodate small number of bays. Distributed can go for huge number of bays. This is one difference. In centralized, it is faster than distributed because there is no two-way communication. It will directly get the current and it will take the decision. Whereas in distributed, all the bay units will send the information to the central unit equipment. So your specific question is about selecting the number of boxes. So when you select R phase separate box, Y phase separate box, B phase separate box, we can accommodate more number of bays. Whereas if you have a very small substation with just 8 bays or 6 bays, you need not use 3 separate boxes. One single box you can connect R phase in a one separate card, Y phase another separate card, blue phase another separate card, and these 3 will work integratedly inside the relay. So the trip logic, the detection logic, everything is going to be same. However, depending on how many CPs you are connecting, how many zones are available inside that relay, based on this, the internal logics, number of lines that we are going to write the logic, what kind of logic that we implement, this will keep on changing. So it's more an architecture based question specific to a MyCom relay. So we have to discuss with the single line diagram and the relay capability in order to give you a very clear answer. But I have just given you a overall idea on how this is done.
Thank you, Doctor, for your answer and your time. We will continue in our break for a few minutes, and then we will start with the next session presented by Mr. Mohammed Rashad from Alfanar Engineering Services. And he will be talking about distance protection and testing for distance protection. Thank you all, and we will continue with you in few minutes.
Thank you very much. Bye-bye.
اوكي حنعطي منه الحين دور منه
Okay, welcome back everyone. We take a little bit more time than intended for the break, but was a well-needed one for everyone to have a fresh start again with us. This session is presented by Mr. Mohammed Rashad from Al-Fanar Engineering Services. Before we start, I would like to remind everyone that shortly after this, we will add the link for registration for day 2 in case anyone would like to register who have not done before in the chat window. So, Engineer Mohammed, please, the floor is yours. Please carry on. And good luck.
Thank you, Mr. Ali. Hi, everyone. This is Engineer Mohammed Rashad, working for Fanar Engineering Services. I started my career as a testing and commissioning engineer, and now I'm the section manager for the technical training in Fanar Engineering Services. Today, I would like to talk about the line distance protection theory of operation, and also I would like to apply for the distance reach test on the 7SD522 relay using the Fraser 546 test kit. So let's start first with the, sorry, where is it? So let's start first with the theory of operation for the distance protection. As we know, the basic idea for the protection of lines, even this one is overhead line or underground cables, the basic idea for the protection was the overcurrent protection. And for example, if we have one line like this one, like this line, which shown here, and we have a fault outside of our line. In this case, what will happen, or what will be the fault current if we have two generators connected in parallel to the same bus and feeding this fault? We know that in this case, the fault current will equal to the voltage over 0.5x, which means x over 2, plus the y, which is the line impedance. It means here we have two impedances, the source impedances plus the line impedance. In this case, we have a certain fault current. So if we would like to adjust our overcurrent setting in the relay, we will adjust the overcurrent setting to be based on this fault current. And this fault current is feeding a fault outside of our zone. So if we, for example, if we said that this fault current is 1000 ampere, 2000 ampere, whatever the fault current is, it means that I would like my relay to don't trip for such current. It means the current fault has to be higher than this value. So in this case, the protection relay would trip the fault in the relay would trip the breaker of the line in case of the current is above this value, which means that the fault is inside my line, not outside of my line. So if we bring a protection relay and we put it here at the start of the line, and we adjust the setting of overcurrent is above the value of the fault current that we have detected in this case. So in another scenario, if we have only one generator is feeding a current and the fault is inside the line itself, in this case, the fault current will equal to the voltage over the impedance, which is equal to the source impedance plus the line impedance. In this case, we can see that the source impedance is higher than the source impedance of the previous scenario. So it means that the fault current here in this case will be less. The fault current here will be less. And in the first scenario, we have set a higher current. So in this case, we cannot clear the fault, and we cannot discriminate the fault even it is outside of my protection zone or inside of my protection zone. So I lost one of the most important features of the protection system, which is the discrimination of the fault, where the fault is. So as we said here, or as we can see from the two scenarios, that the I fault is depending on the generators or the source impedances, which will disturb the overcurrent settings. So in this case, as we said, we cannot discriminate. So the overcurrent is called, in this case, is a non-unit protection. We know that this is the overcurrent is under the non-unit protection, which means the protection which cannot protect a specific zone and can clear the fault fastly. Okay, so in this case, if we would like to use the overcurrent protection, it doesn't mean we cannot use. We can use, but in this case, we have to use the overcurrent with a time delaying, and also we have to use the overcurrent with a time grading. It means time delaying means because I cannot differentiate between the fault is inside of my zone or outside of my zone, so I have to wait for some time delay, and this will be because I don't know where the fault exactly. And time grading, it means that we have a series of lines in my network. So in case of a fault far away from my substation of my line, the nearest circuit breaker will have the shortest time, which will be the first one, and then the next one will be there is a time delay between each line and the other one, so it's called a time grading. But in our protection system for the transmission system with a high voltage and extra high voltage, the fault clearance time is very important to us, and it has to be fast cleared. So instead of depending on the current measurement, we have to depend on the impedance measurement, which means that I have to depend on both measurements, which is the voltage and the current, and divide the voltage and the current. The quotient of this one will be the impedance. So the impedance here will be affected not only by the current, will be affected also by the voltage, which will also be affected by the source impedances. So in this case, if I know that my line from substation A to substation B has a certain value of impedance, so in this case, if the measured impedance by the relay is less than the impedance of the line, in this case, the relay of my line has to take the decision to trip the local circuit breaker and clear the fault instantaneously, or at least with a certain time delay faster than the one in the overcurrent protection. The first idea they used is the impedance characteristics, which is drawn on Rx locus. We have the R is the horizontal axis and the X is the vertical axis, and we are drawing a circle, and this circle with a radius, with the radius equals Z over 2, and or even the radius equals Z. This one depends on the settings or different logics, I mean. Whatever, it means that here we have the impedance of the line is the radius for this characteristics. So in case the fault is inside this zone, the relay would trip because the fault is in my line. But there is some challenges or problems in this one, and the impedance characteristic that the impedance characteristics have, which is this is a non-directional. It means that wherever the fault is in the line side or in the bus side, the relay will respond to such fault and it will trip by the same time delay. So this is have some limitations, or can be used only as a backup protection but not as a main protection. So as a main protection, we have used the MOHU or admittance characteristics, which is based on a shifted characteristics to be either in the forward direction or in the reverse direction. Also, it will be drawn on the Rx locus, and this impedance, the impedance diameter is the impedance of the protected line itself. And this one, or this impedance with the diameter of the impedance of the line, has a tilting angle, or we cannot say tilting angle, we can say that has a declined angle with the line angle. Line angle means 10 minus 1 x over r of the line itself. And by this way, we have solved the problem of the non-directionality of the impedance characteristics. But still, we have one more problem here. Due to the faults with the ground and due to the arc resistances, which appears during such faults, we can see that some faults would be outside of my MOHU characteristics, and this is because of the added resistance to it. To overcome such a problem, we have in our protection relays two angles. One is called the line angle, and one is called the distance characteristics angle. The distance characteristics angle, this is the angle that the relay is using to draw the main characteristics of the distance protection, which is used to decline the characteristics as a total in order to cover the arc resistances. But such solution is reasonable, and such solution can be used in case of short overhead lines or short cables or whatever like that. Why? Because in such cases, the arc resistance is a measurable value and significant value if compared with the line impedance itself. So if we are using long lines, in this case, the arc resistance will have a less effect on the overall fault impedance that will be read by the relay. So here we have some challenges that we agreed that we have our impedance line, our impedance of the line, which is maybe from 0 up to 100% with a certain declined angle, which is the line angle itself, which is equal 10 minus 1 or arctan of x of the line over the line resistance. But during the fault, and what will happen, for example, if we have a fault at the end of the line 100% or at 80% of the line, at 60% of the line, wherever the fault is, and this fault happened with the ground, we have here more resistances would be added for this one. What type of resistance that we have? We have here one is called arc resistance and one is called the tower footing resistance. So the arc resistance plus the tower footing resistance will be represented as a line parallel to the r-axis r-axis of the rx locus. So the total impedance will be read by the relay will be this impedance. In such case, if we have the mode characteristics, which would cover only up to the 100% of the line, here we have a problem and we have a challenge that the relay may not be able to trip for such faults. That's why I'm telling that if we have another relay characteristics angle or distance characteristics angle, we can cover such faults, but just in short lines. But in long lines, we have to modify such characteristics. And we are using, in such cases, the quad characteristics. The quad characteristics here is a characteristics which can be drawn by 4 lines or 5 lines, depends on each relay characteristics. And the most important thing in this one, that each line is independent and can be drawn with different values rather than the other lines are. Okay, so here we can use the right resistive reach with adaptive value and settable value. We can change the setting of the resistive reach in order to compensate for the arc resistance and the tower footing resistance. So this is regarding the right resistive reach. So the right resistive reach here can be extended, as we said, in order to avoid the encroachment, to avoid the arc resistance and the tower footing, but at the same time it shouldn't be high, it shouldn't be big, and also can be limited in order to avoid the encroachment of other load impedances or other load resistances. Okay. What about the upper line, which is the x-axis? We will talk about this one, but up to this point, we can use only the upper line of the distance characteristics as a flat line with 180 degree. But we'll see we have some modification on this one. Okay, anyhow, we have reached the quad characteristics, and by using the quad characteristics, we have also some challenges in general for the distance, even we are using impedance or quad characteristics. What are the challenges that we are facing in the distance protection? First one is the CT ratio and the VT ratio errors. It means that if we have a CT ratio error or a VT ratio error with certain levels of current and voltages during the fault, it means that it will impact the impedance measurement inside the relay. And in such a case, the external fault can be read as internal fault, or the internal fault can be read as external fault. So this is the first challenge. Second one, during the calculations, we have ignored the line capacitance in the impedance calculation, and we kept only in mind our X and R of the overhead line or underground cable. So the ignoring of line capacitance also has an effect over the total impedance that will be read in the relay during the fault, or during the fault with a resistance or without a resistance. There is some impact of the line capacitance will be appear during the fault. And also we are ignoring the overhead transposition effect. And finally, we are ignoring the fault current from the remote end of the transmission system. So in such cases, because of all of these challenges, we cannot use the distance protection as a one zone, and this zone will cover only the impedance of the line. Why? Because this one will be critical, and as we said that any fault is external can be read as internal, and any fault is internal can be read as external due to those four challenges. So in such case, what we'll do, they think about why we are not dividing our distance protection over zones. And the first zone is zone 1, which will only cover 80%, or we can say generally or typically from 65% up to 85% of the line impedance itself. Why we are using like that, as we explained, because we would like to, or we want, and we have to avoid the challenges that we are facing due to the four challenges that we mentioned. So in such case, we are using 80% only of our line impedance as a zone 1 of protection to avoid such errors. In this case, if a fault happened inside this zone, it means that I'm sure that the fault is inside the zone itself and inside the line itself. And in this case, I have to take the fast action of tripping with a 0 milliseconds. So up to this point, someone will ask me, so in this case, we can say that the distance of protection is a unit protection. Up to now, we cannot say yes. Why? Because the unit protection is defined as that we are protecting a specific zone with a specific boundaries and no need for time delaying. Why? Because I'm sure that the fault is inside a typical zone or a certain zone. So the distance protection, you are telling me here that I'm sure that the fault is inside zone 1 and I will trip instantaneously. Yes, you are right. But in such a case, we are talking about overhead line or underground cable, which is protected by two breakers in its two ends. So in such case, if a fault happens inside zone 1 of one side, but outside of zone 1 of the other side, in this case, this relay will trip instantaneously, while the other relay will not trip instantaneously because the fault is not defined as or recognized as in zone 1. So in such case, we cannot say that we are unit protection, because if we are saying we are unit protection, it means that both ends will be tripped. That's why we have the distance teleprotection schemes like the overreach or underreach or blocking scheme, which is used to convert or will used to enhance the distance as a non-unit protection and convert it to a distance unit protection. Okay, anyhow, now we have zone 1, which is 80% over 80% of the impedance of the line with 0 milliseconds tripping time. And we have zone 2. And zone 2, this is used to cover the remaining part of the line. If we saying that zone 1 is 80%, so zone 2 is covering 100% of the line? Sure, no. Why? Because if I cover again 100%, I'm still in the risk that the fault, if inside the line, it can be say so as outside of the line, or if it's outside the line, it can be recognized as it's inside the line itself. So it's the same idea. We cannot cover any zone as 100% only, except in some cases that we'll explain, inshallah, in other sessions. But up to now, zone 2 is covering only 100% of the line plus 50% of the next shortest line. And this is why, because we have to make a coordination between the lines and each other in the network, because I cannot cover up to 50% of the longest line or up to 20% of more of my line impedance. No, it has to be calculated with 100% of the local line plus 50% of the next adjacent shortest line or the next shortest line in the other substation. Why? to avoid the overlapping or to avoid the overlapping between zone 2 of the next line and zone 2 of my line, which will in both cases or in each case it will trip the post lines at the same time. So we have to have a time grading between the line itself themselves. So the first breaker of the next line has to trip first, and then my breaker, in case of this breaker fail to trip or the fault still exists, so zone 2 of R1 here has to extend up to 50% of the next shortest line in the next lines. Zone 2 is not covering only my line, it has to cover my line and used as a backup protection for the next line. So it has to be with a time delayed with a typical time between 250 milliseconds up to 400 milliseconds. So as we said that the distance cannot be considered as a unit protection except if we have another enhancement of the distance like the distance teleprotection schemes. Now let's go back for the upper line of the distance protection. The upper line of the distance protection, which is the x-axis, we said that this is a straight line, but actually this shouldn't be a straight line. It has to be tilted up or tilted down with a certain angle between 3 to 5 degrees and sometimes up to 7 degrees. And this is why, to avoid the tripping during external fault or avoid the tripping during internal fault in some cases. Let's see how these cases are. First one, for example, if we have now an overhead line or underground cable is extended between two substations and the load is fed as a forward load, it means that from substation A to substation B, substation A here, the voltage is a reference with angle 0, while substation B, the voltage here is lagging the voltage of the substation A with a certain angle phi. So what will happen if we have a fault? The fault will be fed from both ends, IA and IB. So in this case, if we have IA as a reference for us, for example, and IB will be lagging for IA. In this case, the total line here, or the total current here will be equal IA plus IB. And this will be lagging the IA itself. So in this case, if we have our characteristics like that, the quad characteristics, the fault impedance will be read by the relay will be IA multiplied by Z of the line. It will be based on the fault is in middle of the line, at the end of the line, whatever. If we can say that, for example, the fault is outside of my line, okay? In this case, due to the fault is fed also from the other side with IB, which is lagging IA, so the effect here of IAB, which is passing through the fault impedance, will be multiplied by the resistance of the arc, we can say arc resistance or fault resistance, multiplied by IA plus IB, so the total fault impedance that will be read by the relay will be inside the same zone. So in case the fault outside of zone 1 in this line or outside my line, actually, the relay now will recognize the fault is inside the zone again, either in zone 2 or in zone 1. But I have a problem in case of zone 1. Why? Because if the fault here is about 90% of the line, and due to the feeding from the other end, and the relay will recognize the fault as inside of zone 1 as per the characteristics shown below. So in this case, if I have tilted the line, the top line or the X line of the characteristics of the quad characteristics, I can avoid such fault tripping. So the new reactance line tilting angle will avoid tripping for such external fault. If we are talking about zone 1 or if we are talking about zone 2. It means that if the fault is inside zone 2 but outside zone 1, it can be recognized as zone 1. So I'm afraid from tripping as a fast tripping with 0 time, or if the fault is outside zone 2 and can be recognized as zone 2, it will make a conflict between two lines can trip at the same time. So in such cases, if we are tilting the top line angle of the X of the characteristics, I can avoid such faults. While if we have another scenario with a reverse load effect, that the fault is or the load is fed from substation B to substation A. In such case, if we have a fault, the fault will be fed from both ends. And if we have IA with angle 0, while IB is leading IA, so IAB will be leading IA. So in such case, if we have the characteristics with the tilt top angle is towards down or flat tilting angle, what will happen? Here we have IA multiplied by Z line, while IAB multiplied by the fault resistance, total impedance will be read by the relay will be outside of the zone. So in this case, if we can tilting the top line angle to up, in this case we can allow the relay for tripping, especially for internal zone. It means that if the fault is inside zone 1 itself, but due to the fed from the other side with a reverse load, the effect of the reverse load here will make the relay at substation A will see the fault as outside of zone 1, and it will trip with a delayed tripping. So in case if we can tilting up the top line angle, the relay can recognize the fault as internal fault and it can trip. The tilting angle here can be, as we said, negative or positive. So in relays in different manufacturers like Siemens, it can apply only the tilting angle of only zone 1, because this is the problem, and the tilting angle will be always down with a negative, and to avoid the tripping for external faults and not to be recognized as internal fault by zone 1 and avoid the fast tripping. While in cell relay, we have a tilting angle for all zones. It will be applied for all zones. While in MICOM relays, we have adaptive tilt angle. What does it mean by adaptive tilt angle? It means that we have a fixed angle, fixed tilting angle, while this angle can have a more value or less value based on the analysis of the fault itself. The relay will analyze the negative and zero sequence currents, and based on that, the relay could recognize how we have to modify the tilting angle up or down to avoid the false tripping. So anyhow, zone 1 will always, or in the relays will always be tilted down in order to avoid the overreaching, while zone 2 could be tilted up in order to avoid the underreaching. Finally, here we will talk about the ground compensation factor, which is most important feature in all distance protection relays, and this has to be considered in all protection relays, which means that if we have a fault with the ground, and the ground could be homogeneous or non-homogeneous, and can be represented by an impedance which is consists of a resistance and reactance. So in such a case, if the line impedance itself, for example, 9.36 ohm with a certain angle, and the fault happened with the ground, in this case, the relay will recognize the fault and calculate the fault impedance as the summation of the two impedances. So the relay will recognize the fault impedance is higher than the impedance of the line itself. So in this case, what will be the action of the relay? The relay will not trip. So all relays have to be equipped with ground compensation factors, could be represented as Kn and K5, or has to be represented as RE over RL and XE over XL. And this compensation factor is used by the relay calculation in order to compensate for the ground impedance. So the ground impedance has to be tested and has to be calculated in order to calculate the factors of the ground compensation, and it can be set in the relay, where the relay will, for example, if we have a fault over a single phase A to neutral, so the relay will divide the voltage of phase A over the current of phase A plus the factor, which is the ground compensation factor, multiplied by the neutral current, which is finally equal N multiplied by zone 1. Whereas the factor itself is equal to the zero sequence impedance over the positive sequence impedance minus 1 over 3. Now let's move to the other one, how we can test the distance characteristics. We have two distance characteristics. One is called, we have two tests of distance characteristics. One is called the reach characteristics, and one is called timing of the characteristics. So we'll talk only about the distance reach. Reach means that we have to assure that the relay characteristics based on the setting of the relay, and these characteristics has to be with certain boundaries. I need to check that the relay will respond to the faults according to these boundaries. We can say like the pickup for overcurrent, but the pickup for overcurrent, we have only 1 point for the current value, but the distance here, we have impedance and we have angle for such impedances. We have 4 lines for the characteristics. So what we will do, I'm using the Fraser 546, and the most important thing and most impressive thing in this one, you can use by your PC as a software, but in some cases, if we are in a pressure, and this is what happened actually in the sites, and you have the frigate itself, so we can, this frigate can be controlled by your mouse, a wireless mouse. You can put it as a USB, and you can use the screen itself as a software of the Fraser automatic test. So I can use the screen and I can do everything step by step. It means that, for example, let's see this one. I'm taking like screenshots of the test I have did with the manual screen of the HMI of the Fraser 546 itself. So first you can choose the test here, the test type, and you can choose between 3 different distance test or test module. You can choose here the test module. You can use the impedance, the free test, or you can say that you can explore the distance characteristics if you don't know what's the distance characteristics, and this can be useful in case you have old relay and you don't know how to draw the characteristics. And finally, we have the impedance characteristics that we will use. After that, if you push this button, you can choose between various protection relays manufacturers, and I will choose the Siemens relay. This is the Siemens relay. After that, you can, this is Siemens relay template. We have many relays in Superposition 4 and Superposition 5 relays. So I can use now 7SD5, which is the Superposition 4 relay, 7SD522. After that, here, it will open for you the whole parameter settings available, same like in the protection relay itself. So you can choose whatever the setting here, the submenu of the settings, and you can either put the setting, you can edit the mode here, and you can put the setting manually, or you can import the file setting from the relay, and you can support the Fraser here supports many types of files depending on the protection relays. Like we know that if some of you are working in maintenance or testing, we know that like cell relay is supporting the text file. The X-ray file can be supported by MyCom, by Siemens relays. Siemens relays are supporting gray file. So we have different types of file. Here we have the CSV, you have the X-ray, you have many files, but I will focus now in the X-ray file. I have exported from the Siemens 7SD5 to with the settings, with the full setting of the relay, and then I can import here in the relay. After importing, as you can see, it will draw the characteristics automatically. And after that, I can choose which type of input or the feedback from the relay. If I'm actually in the testing stage, I can use the dry contact. It will be very easy. During the maintenance stage, here we have in our sites in Saudi Arabia, we have 2 types. Either the output current from the relay is isolated by the test switch from both sides, or the output current is isolated only from one side. So in this case, we have to use either the dry contact or we have to use the voltage contact. So you can choose between here, dry or voltage contact, based on the status of your site. And the input action here, it means that the contact is normally open or normally closed. Finally, we have some settings here you can use for your test, like the pre-fault values, how the relay is testing here with the pre-fault values for voltage and the current angle, how much will be the pre-fault time delay for time injection. And here you need to control with constant current. It means that the relay will change only the voltage, or constant voltage and change only the current, and so on. And here also you have some settings here for line to neutral, line to line 3-phase, and here you can put the, actually this one is imported automatically while I import the XML file of the relay. But here what you have to do, you have to put here the range or the tolerance of the time delay for each zone based on your manual. Okay, but actually also I would like to give you this one from the site experience, that in some manuals, like in cell relay, it's written as a direct, and also in other relays. But in cell relay, it's written direct that for example, the impedance reach or the impedance timing tolerance is equal, for example, 3% at the line angle and 5% at other angles. So during your test, you will make, as we will see, many ramps, some of them at the line angle, some of them at other angles. So in this case, you have to put here the value of the tolerance of the biggest one of the other angles. Okay, and then you can come here. You have from downside here, you can draw the ramps here. Either you can draw it manually or you can use the IEC 6255. You can use many modes like that. This is one mode, and this is mode. This is because I make it manually. If you use the IEC 6255, it will draw the ramps with a perpendicular angle to the characteristics of the distance. The relay will search, the relay here will start with the impedance outside, and it will search or will continue injecting the impedances up to reaching the boundaries of each zone, and they check the fault or the relay picked up or the relay trip according to the angle, the boundaries of the zone or no. Here just is a very simple example, but in the site we have to put ramps in all directions of the protection zone. And finally, we have a generated report by the Frisia from the screen itself. You can save this one over USB or over USB, so you can later print this one or convert it to PDF, and you can print also. So you can save the file of the report itself, or you can use or you can print it as a PDF. Up to now I have finished, and I'm waiting if someone of you have any question or anything.
Thank you very much, Engineer Mohammed, and thank you very much for the time efficiency that you have. We have still some couple of minutes before the next session start, and you have already finished with delayed start as well.
I noticed the time, there is 7 minutes remaining, so I said if someone has a question, we can cover before the next session.
We do have some couple of questions that might require your attention for. For the first question that we have is that does all distance zones are quad characteristics?
Quad characteristics?
Yes.
This is based because we, for example, in Saudi Electricity Company, we are using for all type of fault phase to neutral or ground distance and the phase distance quad characteristics. But for example, in Aramco, we are using for the ground distance quad, but for the phase distance, we are using the MOVO. Actually, quad is very beneficial if we are talking about ground faults. So the ground characteristics has it is recommended to be ground distance to be quad, while the phase distance to be MOVO, except in long overhead line, short lines, and we are afraid from the arc resistance, we can change to quad characteristics.
Okay. There is another question, is that could we draw the characteristic manually?
Yes, sure. Any relay you can draw the, if you know the equations of the lines, it's available in all protection relays, and through the Frisia 546, you can draw the you have the calculation outside. You can draw this one by yourself in the Frisia 546 from the automatic or the manual. You can draw the line by line up to finishing the zone. But as you can see, you can use the impressive feature that you can import the setting file from the relay with all values, because in case you are drawing these lines, maybe you forget the time, maybe you forget the ground compensation factor, but once you have exported the setting file from the relay and imported it to the Fraser 546, it will take into consideration everything in the relay.
Okay, all right. And one last question is that for the reach test, what is your assigned function on your binary output for Z1 pickup, Z2 pickup, and Z3 pickup on Siemens relay?
Again, sorry, again, I didn't get the question again.
I think he's asking about the binary output assigned on the relay itself for Z1
The
pickup,
binary output, yes,
Z2.
yes, no, not pickups. During the test of the distance reach, we are using the tripping, not the pickup. We are using the tripping of each zone. So you can either assign each zone tripping with the same output contact, or you can use the distance general trip. And this is available in Siemens. We have distance general trip. In MyCom relay, no, you have zone 2 trip, zone 3 trip, zone 4, zone 1, like that. You have to take it over, for example, OR gate. In cell relay, you have to choose Z1T or Z2T or Z3T, like that. And you have also Z1BT and Z1GT for differentiating between ground distance or phase distance. This one based on which zones you are checking.
Okay, all right. It seems that we are out of questions in very timely, efficient time. Thank you very much, Engineer Mohammed, for your time and for this very informative and actually enjoyable presentation as well. I myself actually learned a lot from it, and I have tested a lot of distance relay before. So thank you very much for that from myself personally.
Thank you,
So the next session will be conducted by me. It's about line differential protection, and we have few minutes before the time starts. Thanks to Mr. Mohammed Rashad. So I suggest a break for 5 minutes, and then we will continue after that. Thank you all, and we'll see you in 5 minutes. Hello everyone and welcome back with us today. So the last topic in our session today is for the line differential protection testing. And in this topic, I'll try to make it a little bit light and fast for everyone. Since it's the last session and I believe a lot of you are tired, I myself a little bit tired as well, but I hope it's refreshing that I give you some energy to continue with us. So for my agenda today, first I will give an introduction on where or why we use the line current differential from the scheme classifications and the priority scheme being explained briefly and where does it fit in. And then we'll talk specifically about the line current differential, how it's been applied, the setup for the whole scheme, and also some details about the specific restraints or specific limits and settings that we have for line current differential. And after that, we'll talk about concept for testing, give also an example on how do we test that based on real numbers. And in the end, we'll talk about test challenges that we face when we are conducting line differential protection. And as well, in the conclusion, I'll talk about what's coming new and what we have now for this testing requirement. So without further ado, let's start with our introduction, starting with transmission lines. Transmission lines are a very important part of our power systems and transfer the power from generation to distribution, the load. They operate at different voltage levels and they are classified mainly based on their source impedance ratios or SIR and voltage levels. And for some transmission lines that they operate near their stability limits, it is very highly favorable to use a higher speed fault clearance in these transmission lines. So any schemes that introduce time delays for achieving selectivity, it's not really favorable. Usually we want to have 100% selectivity and also a fast tripping. And for that, we can classify schemes for protection as non-pilot based and pilot based. Basically, the non-pilot based ones are like step distance that is mainly used for transmission lines. Like what my previous presenter has explained, Engineer Mohammed, usually using distance zones, using the measuring voltage and current at the same time to achieve that. And it has quite the challenges there as well, like the time delay, the difference, and the calculation errors from the CTs, VTs, relays, and all of what he explained previously. Then we have the pilot-based schemes. Some of them are, I would say, classify them as directional comparison, where they check the fault if it's in this direction or not, or on the forward or on the reverse. And usually they are equipped with a step distance or directional earth fault. And we can classify them as blocking schemes and permissive schemes, where the blocking schemes, they block the signal from going to the other end, and permissive, they send the permission to accelerate the tripping. There are different details about them, but this is not our main topic today. Our main topic is schemes that based on current, and they are could be different number of other things like phase compensation or I'm sorry, phase comparison, charge comparison, magnitude, and phasor comparison as well. I will not go through the details of each of these. Mainly we'll talk about specific ones in them that is mainly used in today modern numerical relays. So these pilot-based schemes, they definitely require a communication between them to be able to be achieved. And more than one relay will be involved from both ends or from different ends of the line to achieve that. And of course, you will have a third, I would say, or additional communication channels that will allow you to turb very fastly with a higher selectivity than non-schemed. So this communication channel is very important, and there has been a lot of technologies used in the past, starting with pilot wires that people use, and then moving to also power line carriers, where they use the line itself to carry the signal using special equipment. And also audio frequency subtones has been used, microwaves for remotely for very short lines, and more frequently nowadays is using a digital channel, usually with fiber optics cabling for a very long transmission distance. So this takes us to the line differential protection. Basically, it's you having your two ends, each is measuring the current from one side, and through their communication channel, which is usually nowadays a fiber communication channel, they will transfer these measured values between them, and also do all the time calculation or time delays get compensated during that using a specific I would say methods that defined mainly by the manufacturers or the philosophy that they are following for that. These line differential protections usually will have characteristic in them, and this characteristic is usually used for differential protection will be mostly was a biased one where they have two slopes. The second slope usually for situ saturation characteristic, but also something maybe known or famous for SER relays is using a ratio-based way, or I would say an alpha plane, where they calculate the remote and the local, and they put it on a plane and get the ratio from it, and define where is the tripping and where is the restraining or stability zones. Our main topic now is to talk about end-to-end testing. What is end-to-end testing? When we talk about that, it is the evaluation of the whole scheme for the protection for fault conditions simultaneously at both or even more than two ends of the transmission line. Everything from the relays, equipment used for communication, interfaces of this communication, all being tested at the same time. This is, you can say, comparison between doing a whole scheme versus an individual components. Yes, it is true that you need to test each individual components, but how they all work together to achieve this also important to be tested as well. So it could be a double-ended line, or even in some cases a multi-ended line, triple-ended line, for example. So what also more in detail we mean, as I mentioned earlier, a whole scheme versus individual components testing. And also another thing when we talk about end-to-end testing is the issue or the challenge of time synchronization. How can I synchronize both ends when I conduct the test to be starting and also operating at the same phase angles or set phase angle all the time. And how can I distribute the time for each end when we are talking about that as well. So these are the main challenges that we need to cover and see how does it work. But one question some people might ask is, why do we do end-to-end testing? And one reason for that is to evaluate these test methods and make sure that even the individual components, once we test each one individually, is evaluated in the whole grand scheme of things. And also it is, you can say, the only way to validate the communication based scheme effectively, where you make sure that it is working based on your expectation and specification. And also it helps you locate issues that single or individual components cannot really see. For example, delays between the communication channels, or when one channel fails, you have two channels and one fail and it transmit to the other one. Really doing just normal testing or just individual component testing might not show you the whole picture like doing end-to-end, full end-to-end testing. So what do we test? The communication-based channel schemes, and also different various scenarios that we require to test, from normal stable loads to when you have internal faults inside your zone, how your protection scheme totally should behave. When this is another question that some people ask, it's whenever you have any new installation, and also we recommend to do this on a regular basis for maintenance testing, any issues, alarms coming in. So also we recommend you to do end-to-end testing. I know it's, and once we go through the details, it's a little bit more difficult to go through it rather than the normal test, but also for troubleshooting, you need to do that. And whenever you have system settings being changed, also testing is required for that as well. So when we talk about end-to-end, the whole picture of the test will look like this. I will have my substation A and my substation B, each one. This is the minimum. Maybe you have even more ends or multi-ended lines. And each one you will have a test set there, and each of or both of these test sets need to be synchronized, and for doing so you need a time source that is taking the time from a reference clock. Usually will be a satellite clock. That's the easiest way to do it. And this time source should have the ability to distribute this time from their internal clocks to the test equipment easily and efficiently without any losses or delays. So if we want to compare this to a non-synchronous test, a non-synchronous test, you will only connect to one end and you will do all your testing to it. So your communication media will not be a part of your test, only maybe the equipment or the device on that end will be tested. While in a synchronous test, the whole scheme will be tested, your two relays and also your communication media at the same time. So for testing methods, we have ability to create a states playback, where we create a states. For example, this is a very brief and simple example, is to create a pre-fault and then a fault state and then a post fault state. In a pre-fault, you will inject currents that are in normal load conditions, and then in fault you will simulate a fault inside the zone by creating currents that drainage inside your protected zone. And then in the post fault, you can reset everything to normalize again after the relay trips. Another test method is to use an already created fault before using fault recorders and play back that fault. And this can be done using synchronization as well, where you can take the faults from both ends, what each end correspond the fault for it, the fault currents for it, and play back both of these faults at the selected set time for synchronization. Of course, all of this will require you to have a GPS receiver that can synchronize to satellites to get the time and dates properly from them. The satellites, they're usually, what is most common is to use 24 satellites installations, and this receiver should be able to track all or any of these satellites to get time, date, and also position and altitude information from these satellites to be able to achieve a high accuracy of time synchronization. And of course, this gives you a timing modes, either a static timing mode or a dynamic timing mode. Now, once this GPS receiver have obtained this time from the satellite, you need to be able to distribute the time to your test equipments. This time signals, there are different standards for distributing these times. I will only explain here two, just to give you an example of what's available out there. We have first IRIG-B. It's an industry standard that use a serial time code, standard serial time code that repeats its data once per second, and this data could be in different shapes or waveforms, either modulated or unmodulated. Different formats can give you the time only for in seconds, or seconds, minutes, hours. It can give you the time and the date at the same time. It really depends on the application that you use and what's available for these equipments. Another way to distribute these times to the test equipment is to use something we call POP, or programmable output pulse. It's basically just a pulse with a pulse width that will be issued by your time source to your equipment at the set time. You can make it as a one-shot mode or a repeated shot mode with a repetition duration for that. It really depends on what cases or test scenarios that you are planning to test. So for testing in general, this is a general steps that you will do for the test. You will first isolate the system, connect your testing equipment. And a very important step that I always encourage people to do when you are testing protection systems, whether you are doing end-to-end or not, is to do a wiring check. It's really a very important thing to do. And then put your protection devices or whole scheme in a test mode. And after that, you can generate or play back your test scenarios. So for testing, these test scenarios are also from the point of view of non-synchronous and synchronous test scenarios. For non-synchronous, where you only test one end or single end, you basically can do very basic testing, like pickup test, maybe timing. The communication will not be involved in this. But when you have the two ends synchronized, you can do not only the communication, but also other things like simulating an internal fault, validate your characteristic, and validate your communication and how much delays it introduce in the overall trip times. So an example for that, if we took, for example, an alpha plane with the following setting, a pickup of 0.72 per unit value, and a differential element with a radius of 6. This element is the radius R shown here for this alpha plane. This is the stability area. Anything inside this calculated by the relay algorithm will be considered stable and the relay will not operate. Anything outside this area will be not considered as stable and the relay shall operate. So basically for this characteristic, you have two settings, the R and the alpha angle. Of course, there are more additional security issues, but for simplicity, we will don't look at this at the moment. Then if I want to do non-synchronous test, or I would say a single end test, I can do a pickup test just for the pickup element. But if I want to do the testing from a synchronous end or end-to-end testing, I can do much more from that. I can, based on that, do a fault, pre-fault for both ends and test the limits of the, for example, the radius test and also the alpha angle test as well. For example, for the radius test, I can start from inside my stability zone and going outside my stability zone by creating a synchronized ramp. We can do that either manually or automatically in the software. And also I can do for the inner arc as well, something like this to test that inner arc as well. For the alpha angle, I can also just change the angle boundaries for that based on my setting. In this example, it's the angle is 195. So divide that by 2. I can test the boundary angles. They say minimum and maximum angles by just generating these fault conditions. As well, in the end-to-end testing, I can create just a normal internal faults, checking that everything is working correctly, or I can create a stability conditions that in these stability conditions I can check what happens, for example, with the communication channels. If anything happen, if a failover, if a channel having a certain delay that the device is considering it as failure, or it's reverting to a secondary channel that is being used. All of these conditions I can verify, validate by only using end-to-end testing. So what considerations or challenges that I have that I need to consider? For example, I can consider a breaker simulation a challenge for us in this test. If I can't do it properly, I can fault selection, consider it as an additional checks as well. For example, faults at different locations of the lines, like 50%, 100%, 5%, how the whole scheme will react to it. Different fault types, 3-phase, phase-to-phase, phase-to-ground as well. Maybe one breaker fail at one end, what the whole scheme will refer to as well. And some common reasons for the test to be fail is maybe you have some time delay between the two ends, like the communication channel is too long, or the communication equipment is not up to date, or having any issues or difficulties can be detected with this. No time synchronization settings corrected between the two ends can also run the test to fail, and also incorrect injections. So the calculated value for the test scenarios are not according to the appropriate fault types or appropriate to the other end. It could also result in a failure of this tests as well. So from Megger, we have the SMRT and the Freya family of relay test products that can achieve this requirement for end-to-end testing. And these equipment are being updated continuously to provide the better or smooth user experience all the time. And also for the time source solution, we have the MGTR2, which is a Megger GPS timing. It's a time clock that utilizes satellites accuracy to get an accuracy of 100 nanosecond within a few minutes of startup. And generally, we will use the IRIGB serial time code output to distribute the time to the test equipment, but can be used for other application as well, as since it's a general time clock. And as for the software, right now we have more of, I would say, a manual way of doing the test, but in the future, hopefully, it's in beta version right now, we have the new line differential tool that will be acting similar to the existing transformer differential generator differential existing in our test software RTMS. This tool will automate a lot of things for the testing. It will calculate the values based on the setting applied in the relay, or based on the philosophy that's been applied, for example, for the slope test. I don't have all the details and what capabilities all for this new line differential tool, but it's existing in beta version. I have seen it myself, and also I can assure that it will conduct both the stability test requirement and also the what they call it, the slope test requirement as well. Maybe additional features or other things taken away from it, but these two at least definitely will be available. So thank you very much for attending with us today. We have reached the conclusion of our session for the line differential testing. I hope I have not taken a lot of time from you for that. And also a quick review on our conclusion. Discussed both first the non-pilot schemes and pilot schemes. The line differential protection, how does it work, and some of the methods and characteristics to be applied. And then end-to-end testing, just quickly we run on the surface of it. And also some of the challenges that we might face, like accurate time signals, delays, communication problems and issues, what test values or correct test value injection, and in the end, knowledge of protection scheme in general. These are some of the references and acknowledgement to Sugeesh Koibar for preparing this presentation. Thank you very much for that. I hope all the best for you. So I believe now time for some questions. Check the questions available. So some question coming to me directly, asking about can we use different time distribution method like the BTB standard for time synchronization? Yes, you can use that, provided that the test equipment accepting this BTB. For anyone not understanding the BTB, it's a short name for Precision Time Protocol. It's based on IEEE standard, IEEE, I believe, 1588. It's using a network Ethernet way of distributing the time between devices connected to a network. I believe it requires a special networking equipment or networking switches. I believe they call it a transparent switch to be able to transmit this BTB signal without any delays or additional communication delays. But yes, you can use it depending on your test equipment. However, for the Freja and the SMRT, it's still not implemented in their Ethernet ports right now, but in the future, definitely will be considered for that. Hello?
Yeah, maybe I can comment.
Yes, please, Andrea.
But hi, Andrea from Andrea Bonetti from Sweden. Thank you, all of you guys, for a fantastic presentation, very enjoyable. And I have just a short comment about PTP for our test equipment. You can use any PTP slave, the so-called PTP slave, which is an equipment it's not a translator, it's not converting the PTP message, synchronization message from Ethernet into a pulse per second or IRB. It is itself a clock. It gets synchronized with the PTP signal and provides a pulse per second signal or IRB signal. So there is no time delay between the PTP signal and the output of the slave. And then you are safe. I think this would be the most simple solution for any type of test equipment, because pulse per second IRB, they are quite easy to handle with a BNC cable, etc. So that was only my comment.
Yes, thank you very much for this comment, Andrea. Another question is that what tests can be done with this new beta line differential tool? As I mentioned earlier, I don't have all the details right now to confirm or deny anything. But from what I understand, that most likely the stability test and also the slope test will be implemented in this new tool. I still don't have a concrete date on the release, but hopefully we in testing and validation state, I believe. After short amount of time, it will be released, hopefully. I hope there is no issues or anything that can hurdle that. I believe we are out of questions. Thank you, everyone, for joining us today. And thanks to our speakers and panelists who have joined us from all over the world. And for all the participants, there will be a certificate at the end of this conference. And I believe the recording will be sent to you in a few days by the WebEx system. If you have any questions for our panelists, we will leave the session open for until the end duration. But please feel free to leave anytime. But before doing that, I would like to remind you that there is the second day registration link is available in the chat window. If you just go ahead and register in that, we have very nice topics to talk about tomorrow, including sampled value testing, digital twin will be done by Andrea Bonetti, and also the traveling wave technology for protection and fault location systems. So thank you all. and I hope you have a good day.
Yes, have a very good afternoon, everyone. Very good afternoon, everyone, and see you tomorrow. Can you see me? Oh no. There it is.
No, not yet. Oh yes, now I can see
Okay.
you.
That's because I covered my camera. Okay, guys, I think it was a nice session with the 4 topics. Quite interesting: line differential, distance delay, and power swing, and the bus bar protection, which are bus bar protection. I think Dinesh would have kept talking for another couple of days rather than 1 hour. This is so huge topic. That's definitely so. We have to cut him, unfortunately. So
Yes, I myself learned really a lot, a big deal of information in the short time that he got just talking about bus bar differential protection.
you can always invite him in Bahrain if it is open to commit.
Yes, sure.
Okay. All right, everyone. Have a very good afternoon, and see you tomorrow.
Thank you. Thank you, Mauro.
Thank you. Thank you very much for organizing all of that.
Should I close the session?
No, Sanjay, we can leave it for a few minutes if anyone have any questions, and we can maybe answer it immediately for him, or I believe it's a very long day.
Ali, if you want, can you hear me?
Yes, yes, we can hear
Okay,
you.
no, because there are many buttons here to press and stop video, start video, mute, unmute. If I would like to say, if any of you guys, how many people do we still have online? That's also an issue that I am not able to handle.
I believe
we
more
have
than
7.
50.
Oh, we
Yeah.
have more 67. I see. Okay, if
Still on.
would ask if anybody has any comment or any question, but could be also a comment or suggestion for us, please. I don't know how this can be handled, but I'm pretty sure we can give you the microphone. You just unmute yourself probably and start the video and come out.
Yes, this is actually something we never tried before, and I've been trying to do before something like this to open the mic to attendees, make it even more open and easier for them. We never done that before. We don't have the experience of it, but I believe it might have its own difficulties really for doing that. But we can try now since it's an open session.
We can even try. Yeah, we can try. So we also can train for tomorrow. If
Exactly.
you don't have, maybe they don't have the unmute button. This is what you mean, Ali?
I believe we can maybe do that. I'm not sure. I would believe the hosting guys, the Sanjay with us here, can give more better answer on that.
Yeah, I mean, any participant would like to ask any question, just raise your hand so that I can unmute them.
Raise your hand.
Yes, there is a button for raise your hand as well.
I don't have the button because I'm panelist. Maybe.
I think it is there. Just go to the panelist or participants and then click the raise hand button.
I found it. A very, very small button. This is a very small button. Yeah. Raise hand. Yeah. Or you can do like that. It's much easier, you know, Ali.
Yes, true.
Yeah, so nobody has raised.
You can go on with your question.
No, I just wanted to thank you all. It has been a great session, and yeah, look forward to meeting you all tomorrow also. So I just wanted to check that, as you said, that just to check the raise button. So I just thought let me have a try for that. Yeah.
Yeah,
So thank
you're
you.
very welcome, Sam, for that.
Thank you.
I believe we have another raised button, Sanjay. Can you open the mic?
Yeah, hi Ibrahim. Go on with with your questions. I think he has just asked a question in the chat section.
Oh, okay. Yeah, I can find it. Yeah, found it. He's asking for load encroachment. I believe this is related to distance protection. Z0 along with the load angle are required in certain relays. Technically, there would not be any I0 or V0 under heavy loaded condition. So why it is required or necessary? For example, it is required in 7ST522. Unfortunately, it seems that Mr. Muhammad Rashad have left the session. Anyone from the panelists would like to answer this question, please feel free to do that. We cannot hear you, Andrea. I believe you are speaking. Yeah.
I told you, too many buttons. Maybe I can try to explain the question if I understood it well. If you have a single phase stripping, for example, it's not true that you don't have a zero sequence current because you open one phase and during the that phase, at that time, you have two phase loads, and this two phase load is creating a zero sequence current. So there are complex situations where you have to consider the load encroachment also for single phase to earth loops. I say loops characteristics. And that is where a zero sequence impedance of the line enters because it's just a description of the line. You can have a Kn factor zero sequence impedance, or you can call it neutral impedance, whatever. It's just a description or mathematical model of the line. But when you have single phase faults and you have single phase opening, during that time of the auto recloser, you must be able that you don't enter in the load encroachment because you would have created three-phase strip and you would kill auto recloser. This is one of the most typical situations of missed auto reclosers during. You understand what I mean with missed auto recloser? Should wait 1.5 seconds for single phase auto recloser, but it is killed by the three-phase strip because of the load, that two-phase load that enters with the zero sequence current. I hope I managed to explain a little bit if I understood the question, but otherwise, just take the mic and let's discuss if I misunderstood. It's difficult to answer 3 lines.
Unfortunately, I believe he have a problem with the mic that he's using. He cannot.
Okay. Yeah, I see that. Yeah, I see that. Okay. Did I answer you somehow? You are Ibrahim, yeah. Typing, probably. Yeah. I think he said okay, or I think I
Yes, and he understand the case.
okay.
I actually have that question one time as well. Why we required all this information for example, power swings, or for zones for power swing, or for load encroachment. So it does it is required based on this very, I would say, narrow or slim chances of cases that could happen. So it's required for this.
Well, you know, when you Ali, when you are supposed to have a single phase auto recloser, it is supposed also to be successful, and you remain with the three phases open, you get a phone call. So that is not a nice situation. So the auto recloser is not a protection function from the strict point of view, but it protects your load transmission. And in 61A50, you can see the auto recloser logical node is called REC. R means protection related, so it's very strictly protection related protection function. And missing the auto recloser in today overloaded lines is it's a big issue. It's a big issue. So a lot of efforts are put in place to make auto recloser as dependable as possible, I would say, and not killed by the relay itself.
To be honest with you, I never considered before. Maybe this is something new for me. That auto recloser is a protection function. I mainly considered as, say, control functionality that's required. But now that you put it like this, it is considered as a protection function now. From
Yeah,
my perspective.
it's not a protection function in the way that you see there is a big power current and everything will burn. I have to open the breakers. Not in that case, but it number one protects the stability, because if you put a single phase auto recloser in place, you protect the stability of the system, and then protects your load exchange, because you make the lines because you want to sell to transfer the energy. So both auto recloser and synchro check are definitely important protection function. Even pole slip can be considered a protection function, not only because it is a drastically protection function for your machine that starts to jump and it gets broken, it's also protection function for the system stability. In Russia, the pole slip protection, it counts how many slips the impedance runs, and the more far away from the machines you are, the more slips you allow, and then you selectively open some breakers that you know which ones you have to open. You must have a good competence of your system to keep the stability of the system, separate the system in smaller pieces to keep it stable. So there are different type of protection nowadays, yes.
So we still have around 10 minutes as well. If anyone have any questions, we have experts here that can really, I would say, dive deep even with you for that. You can basically just raise your hand and we'll open the mic for you to make it even easier to ask this question.
Let me just say that there are no stupid questions. In the worst case, you get stupid answers, but we are used to that, so we can manage stupid answers. But please make your questions, and if you don't have any, I have one, which is not only really a question, it's a comment, but let's wait for you first.
I have, I would say, I wouldn't call it a stupid question, but a question that I never really got an answer for. I have asked it before to some people. So in quadratic or quad characteristic and distance relays, you usually have your zone in the XR plane, also covering the second quadrant, slight area after the 90-degree. I am asking, why is this added to quad zones? Is it just by design like this, or there is a specific reason for that?
I have some parts of the answer for sure. There are not only single phase towards false, not two phase towards false. Sorry, two phase false or three phase false. There are phase to phase towards false, and you end up there. So much you open, you have to run power system faults with power system network simulators with superimposed load to decide how really you want to open the directional lines of your forward direction. What is forward and what is reverse has always been is one of the most difficult things to do. Actually, I think it's more difficult to design the directionality of the power system fault than the reaching in terms of impedance. And there are many relays from different manufacturers that have a different competence or reach the different results, also because it depends on the numerical calculations they do. So that's why you see different angles. But one of the clear reasons is for face-to-face towards faults, where there is no standardized mathematical model in terms of voltage and currents, and also superimposed load. You may end up there.
What do you mean exactly by superimposed loads?
Yeah, that when we do fault, when we test a protection relay with the characteristic, we are making zero current in the healthy phases. But when you are in the power systems, you have the load. So those currents, if the load is heavy and the fault resistance is high, which means the fault current is small, you can have a fault current in the order of magnitude of the load currents. And then there's nothing we do with the test sets, and we should never do that because it's not meant. But when you do the type testing or you do factory acceptance, no, not even factory, then when you do the protection algorithm, you have to take care of that, because if there is a fault and everybody sees where the fault was and the relay didn't trip or tripped wrongly, again, you get a phone call. So when the protection algorithm is very complex. It's not only characteristic testing, etc., but we do commissioning and maintenance testing, so we end up there, and we have also standard that declares how the characteristics, doesn't say how the characteristic looks like, but says the mapping of the impedance into the voltage and currents. So there was no standard many years ago. Now there is, at least, so we know when we say 1 ohm what we mean in voltage and currents. And that is where we stay with our tests. We don't want to do type testing. But of course, the protection algorithm is very, very complex. It's not based on those tests.
Thank you for that explanation. I mean, it's a very big and wide field, really, protection testing.
If you, I can just challenge, if you, since I've been working with post-fault analysis many years, and especially distance protection, you can be wondering, but if impedance protection is not based on impedance, it's also based on impedance. We use an impedance plane to explain to what the line distance is, a fault resistance, but at the end, impedance protection runs still on voltage and currents, and sometimes uses also impedance to manage a lot of things. That we can explain it in the impedance plane, but it's not really working there. So you can have a point in the third quadrant, which everybody would say it's a reverse fault, and the fault is in forward. This has happened because the directionality is not in the impedance plane, and the distance, yes. So it's very complex object. And my comment that I had, I'm happy that you have asked about impedance protection, is yes, we don't have to learn the protection algorithms, all the manufacturers, we should never do that, because next week they have done something else. You learn it, and next week they've done something else. It's always improved. We have to stay as much as possible at the power system level with the simplifications we have. And please consider that there is a standard on distance protection, IEC standard, which is a 6255-121. It's now, I think it was 2014, so it's now 7-8 years old. And maybe I can make the link. Tomorrow, I will, when I learn this tool a little bit better, tomorrow I will put the link to this standard so that you can have it.
Huh.
Because if I go on, hello, you are almost ghosty.
That's our colleague Hussein Jafari from
Yes.
Systems.
So you are in the office, guys.
Yes, we are in the office at the moment, actually. But thankfully for noise cancelling, it is a busy environment around me. But you cannot hear anything, I believe.
No, nothing.
Yes,
Wow.
technology. So things are improving all the time. And one question that I always have and would like to know, and I know it's maybe difficult, but I don't want to make it until tomorrow, is for IEC 61850. From what I understand, and correct me if this is wrong, the testing part 10, is not fully comprehensive, or I would say ready. It's still under development or still need much improvement.
But the testing part 10 is not for us. It's for KEMA that are making the A or B certificates for IC 650. So for the testing parts, you have to, this is my strong personal opinion. It's personal opinion, which is also strong. IC 650 is a standard that started many years ago as a substation automation standard for reasons that were introduction of digital technology into substation environment. No, these relays, digital relays, were not able to talk together. It was jeopardizing all the possibilities. So there was a need of interoperability, and that was the main factor that was driving the standard was interoperability. But now it has been so much accepted by many others that don't do substation automation that I see 650 standard as a big umbrella that say, guys, if you want to use numerical technology where you have some measurements of voltage and currents, etc., use 6150. But then you have to apply it. And now we go back. Where do we apply it? In relay protection. Where do we apply it? In a speed control, turbine speed control. Where do we apply it? In hydro power. When do we apply it? In smart grid. Smart grid is not really relay protection. It's related to it. But so at this point, we have to split the 6150 standard into the different application areas and go to the tech. Now I'm talking about IC world, and go to the technical committees that deal with that application area. For relay protection is TC95. For smart grid is partially TC95 and many others. And say, okay, what do you want to do with that standard? I want to protect the power system. Okay, use it that way. And forget about paragraph 10 or clause 10, how it's called. And there you go to us, which I'm part of the TC95, and you ask us how, and I can only answer, I don't know yet. I'm sorry, we don't know yet. We are writing a technical report, and we know a lot of things, but the standardization is the you say, okay, our competence has reached this level. Let's put the point on that. And then we have to decide which level we have decided before we put in the technical report. So We are writing a technical report on how to do the performance of process bus and goose, etc. for relay testing, but we are not ready. So there are a lot of things that we know, but they are not formalized. We hope we will be ready this year or next year with this technical report. But what I say, it's not really only that you read the standard and you make a protection of the substation, or you read the standard or you make a smart grid. You have to apply the standard for the concepts you need. So I let you know that there is an article on electrical tester on that, by the way, which is the latest. Well, I was almost forgetting. And he's talking really about that, about this new technical report that is coming out from the Relay Protection Committee in IC. I know you are in Middle East, have the luxury, you can decide. Sometimes I use IEEE, sometimes I use IC. We know we use IC in Europe, but on the other way, IC and IEEE are cooperating more and more and more any time. So 15, 20 years from now, I believe there will not be any difference between IC and IEEE. Cooperation started more than 10 years ago.
Hopefully they become more integrated together to be able to satisfy
you
both.
see, IEEE 1588 is now IC 650-9-3.
Yes,
Comtrade is a dual logo standard. I mean, we go in that direction, definitely.
I mean, the world have become more of like a small village, worderization, or I don't know what's the word for it. But we are becoming more and more and more connected. So can't have standard for here or here. It's to be working for all.
Yeah, I think it will happen.
Hopefully. I believe we exceeded the time limit that we set for everyone. Thank you everyone for joining us today, and thank you, Andrea, for your quick insights that you provided at the end. Hopefully we'll see you tomorrow at the same time, starting 10 a.m. +3 GMT time, or Bahrain time basically for me. I hope you all have a nice day and see you tomorrow. Bye bye.
Thank you. Thank you very much, all of you.